Let's travel back 600 million years to an era when our planet was just recovering from an icy nightmare. Imagine a world that, not long ago, was a gigantic ball of ice, frozen solid from pole to pole. Scientists call this period Snowball Earth, a time of global glaciation when life itself seemed frozen in anticipation. But now, the ice was retreating. Relentless volcanic activity over millions of years had pumped greenhouse gases into the atmosphere, and the planetary furnace was slowly heating up. Temperatures began to rise. With a deafening crack, the gigantic ice sheets covering the oceans began to crack and melt. Water, trapped for eons, was once again free. It was a time of great change, the dawn of a new era, when the planet itself was about to become the stage for the greatest revolution in its history, a revolution of life. The world of the Ediacaran period we find ourselves in is completely unrecognizable to us. The map of the planet would look completely alien to modern humans. The continents clustered together in the southern hemisphere, forming several enormous land masses. The ancient supercontinent of Rodinia, which had dominated the previous era, had long since broken apart, its gigantic fragments drifting slowly, obeying the invisible dance of tectonic plates. Between them, new oceans were born and expanding, their warm waters flooding the edges of the continents, creating endless shallow seas. Its enormous compound eyes gave it a nearly 360-degree panoramic view, allowing it to instantly spot both potential prey and threats. 4 powerful wings, powered by complex muscles, enabled it to maneuver in the air with incredible speed and precision. In the skies of the Carboniferous, Meganeura was the absolute king, a ruthless aerial predator. It snatched other insects in mid-flight with its powerful jaws. Its life cycle began in the water. Meganeura larvae, like their distant descendants, were fierce underwater hunters, and only after growing up did they emerge onto land to spread their wings and rise into the sky. And on the forest floor, among rotting tree trunks and ferns, crawled a true monster, Arthropleura. This gigantic centipede grew up to 2.5 meters long and almost half a meter wide. Just imagine, an invertebrate the size of a small car. It was the largest terrestrial invertebrate in the entire history of the planet. Its body, composed of many segments, each with a pair of legs, was covered in a tough, shiny shell, reliably protecting it from its few predators. This colossus fed on rotting vegetation, fallen leaves, and rotten wood. Another nightmarish hunter lurked in the shadows of the giant plants. Pulmonoscorpius, a massive scorpion reaching 70 centimeters in length. It combed the undergrowth in search of prey. Silurian placoderms were still quite small and primitive, but they laid the foundation for the group that, in the following Devonian period, would give rise to the largest and most ferocious predators of their time. While this evolutionary drama unfolded in the oceans, a true revolution was brewing on land. The Silurian period marked the first time life truly took hold on the continents. Primitive plants, which had tentatively emerged at the end of the Ordovician, began to evolve and colonize new territories. The first vascular plants, organisms with specialized tissues for transporting water and nutrients, emerged. Cooksonia, one of the earliest known vascular plants, was a tiny creature, no more than 5 to 10 centimeters tall. It consisted of a simple, forked stem, covered in a protective waxy film. At the ends of these stems were sporangia, tiny sacs filled with spores. Cooksonia had no true roots. Instead, it had rhizoids, simple thread-like appendages for anchoring itself to the soil and absorbing water, nor leaves. Photosynthesis occurred directly within the stem itself. But despite their apparent simplicity, Cooksonia and its relatives achieved something incredible. They were able to survive in a completely hostile environment, living permanently on land, enduring the desiccating air, extreme temperature fluctuations, and the absence of a constant water source. Their vascular system, a veritable internal plumbing system consisting of xylem for water transport and phloem for sugar transport, allowed them to transport vital resources from the base to the upper parts of the plant. This was a critical invention, without which the emergence of large land plants would have been simply unthinkable. By the end of the Silurian period, more complex plants had emerged. Baragwanathia already reached a meter in height, and its stem was covered in simple leaf-like outgrowths. It was one of the first lycopods, a group that would later, in the Carboniferous period, form giant forests. Zosterophyllum was similar to Cooksonia, but its sporangia grew along the sides of the stem rather than at its top. Rhynia was more branched and formed dense thickets in damp, marshy soils. These early pioneers of land began their great march. Let's fast forward millions of years to the shores of ancient rivers, lakes, and seas. Here, at the water's edge, where the earth remained perpetually damp, a quiet but momentous revolution unfolded. The first plants, these pioneers of land, couldn't venture deep into the continents. Their lives were inextricably linked to water, as they required moisture to reproduce. Like modern mosses and ferns, they relied on spores, which required an aquatic environment for germination and fertilization. Yet even this modest presence on land began to change the face of the continents themselves. Imagine their tiny roots and rhizoids, thread-like appendages, gnawing into the bare rock, slowly but surely breaking down the stone and accelerating chemical weathering. The organic acid secreted by these pioneers acted as powerful solvents, liberating valuable nutrients from minerals. When these plants completed their life cycle, their remains didn't vanish without a trace. They accumulated layer after layer, enriching the mineral dust with organic matter. Thus, gradually, the first true soils in the planet's history formed, no longer just crushed rock, but a complex cocktail of minerals, organic matter, water, and air. But the plants weren't alone in their great exodus to land. Other life forms also came ashore with them. Fungi, which had established themselves on land as early as the Ordovician period, were now experiencing a true flowering. They entered into remarkable symbiotic relationships with plants, forming what we call mycorrhiza. This association was beneficial to both. The mycelium helped plants absorb minerals from the soil and, in return, received nutritious sugars from them. Such partnerships proved critical for the conquest of continents. Following them, the first animals, arthropods, began to crawl onto land. These tiny creatures were likely the distant ancestors of modern centipedes, spiders, and insects. They were miniature, no more than a few millimeters or centimeters in size, and fed on organic debris, plant spores, and fungal filaments. It's possible that some of them had already become the first land predators, hunting other small invertebrates. One of the earliest known land dwellers is Pneumodesmus, an ancient millipede from the Middle Silurian. Its fossil caused a sensation as it preserved traces of spiracles, special openings for breathing atmospheric air. This was irrefutable evidence of its terrestrial lifestyle. This millipede was tiny, about a centimeter long, and most likely fed on rotting vegetation and spores. By the end of the Silurian period, the first, albeit primitive ecosystems already existed on land. Low-growing plants covered the damp banks in continuous green carpets. Myriads of tiny arthropods swarmed among this emerald growth, feeding on both the plants and each other. And underground, fungi performed their eternal work, decomposing dead organic matter, returning nutrients to the soil. These were only the first tentative steps, but they laid the foundation for the future conquest of the continents. Meanwhile, in the seas of the Silurian period, life continued its grand experiments. Crinoids, or sea lilies, had fully recovered from the catastrophic extinction of the Ordovician. They once again covered the seafloor with dense, swaying forests. Their long stems could reach several meters, raising a crown of feathery tentacle-like arms high above the seafloor. Currents carried their food, plankton, and organic particles, which the crinoids filtered from the water. Entire limestone layers in Silurian deposits consist of fragments of their skeletons, testifying to the truly incredible abundance of these creatures. Graptolites, enigmatic colonial animals that resemble bryozoans, but are actually chordates, thrived in the Silurian seas. These organisms formed entire colonies that either floated in the water column or were attached to the seabed. Their skeletons resembled saw blades or bird feathers studded with numerous tiny cups, each housing a separate organism. Graptolites were filter feeders, and their fossils are so numerous and diverse that paleontologists still use them to accurately date Silurian rocks. Transparent, almost invisible jellyfish and comb jellies floated in the water column. Their soft, ephemeral bodies are extremely rarely preserved as fossils, but the few successful finds we have attest to their great diversity and abundance. Worms of all kinds burrowed through the bottom sediments or floated freely in the water. Some had learned to construct durable tubes from mineral particles, gluing them together with their own secretions. Mollusks continued their evolutionary diversification. Bivalves colonized ever-new habitats, from shallow lagoons to the murky depths of the continental slope. Gastropods, or snails, demonstrated an incredible diversity of shell shapes and feeding strategies. Some were peaceful herbivores, scraping algae from rocks, while others evolved into ruthless predators and scavengers. Echinoderms, sea stars, brittle stars, and sea urchins continued their development. Sea stars were active predators, capable of using their muscular strength alone to pry apart the shells of bivalves and suck out their contents, turning their stomachs inside out to do so. Brittle stars moved swiftly along the seabed on their long, flexible arms, scavenging organic remains and hunting small animals. Sea urchins, meanwhile, slowly crawled over rocks, scraping away algae with their powerful jaws, resembling a complex mechanism. By the end of the Silurian period, the planet's climate had become much more stable. The great ice age that rocked the world at the end of the Ordovician was a distant memory. The planet was warm and humid, with high levels of carbon dioxide in the atmosphere. Oxygen levels continued to rise slowly, though they had not yet reached modern levels. The continents continued their eternal drift, slowly changing the contours of the world. Laurentia and Baltica were inexorably drawing closer, preparing for a monumental collision that would, in the next period, give birth to new mountain ranges and forever change the climate. The oceans of that time lacked giant reefs like those found in tropical waters today, but life was thriving. Trilobites crawled along the bottom, eurypterids ambushed seaweed beds, and giant nautiloids patrolled the open waters. The seafloor was carpeted with a living carpet of brachiopods, bryozoans, and crinoids. Jellyfish and colonies of graptolites drifted through the water column, and the first-jawed fishes darted through this world, hunting small prey. On land, green carpets of primitive plants like Cooksonia and Asteroxylon slowly but surely spread across the continents. Tiny arthropods crawled between their stems, and fungi extended their invisible hyphae through the soil, decomposing organic matter. The sun illuminated these simple yet vibrant landscapes, and for the first time in Earth's history, its continents began to turn green. The Silurian period was a time of rebirth after a global catastrophe, a time of bold innovation and evolutionary experimentation. Life once again demonstrated its remarkable resilience and adaptability. The mass extinction at the end of the Ordovician devastated the planet, but those that survived began to rapidly evolve, filling the vacated ecological niches. The emergence of jaws and fish opened entirely new horizons for vertebrates, and the emergence of plants and arthropods on land marked the beginning of the colonization of the continents. By the end of the Silurian, the planet was ready for the next great act of its history. Plants on land grew taller and more complex. Fish in the oceans grew larger and more diverse. Arthropods explored new worlds. The stage was set for the Devonian period, a time that would witness the emergence of the first forests, the emergence of vertebrates on land, and such an incredible proliferation of fish that it would forever be known as the Age of Fishes. 14 million years ago, one of the most dramatic events in the history of life on Earth began. The Devonian period became the scene of incredible transformations that affected both the oceans and the land. Fish reached unprecedented diversity and size, becoming the undisputed masters of the seas. On the continents, tiny green stalks evolved into veritable forests, their canopies towering tens of meters. And most importantly, vertebrates emerged from the water for the first time, taking their first tentative steps along ancient shores. It was a period when the world was transformed beyond recognition, an era that laid the foundations for all future terrestrial ecosystems. The Devonian continents continued their slow but inexorable movement. Laurentia and Baltica finally collided, forming a single supercontinent, Laurussia, also known as Euramerica. This monumental collision raised massive mountain ranges that were the distant ancestors of today's Appalachians and the Caledonian Mountains. To the south lay the gigantic Gondwana, encompassing the territories of what would become Africa, South America, Antarctica, Australia, and India. Between these continental giants lay vast oceans, Panthalassa, which covered most of the planet, and the smaller Heic Ocean. The climate of the Devonian period remained warm and humid for almost the entire epoch. Polar ice caps were non-existent, and high temperatures were observed even in subpolar latitudes. In the tropics, water temperatures could reach 30–35 degrees Celsius, creating ideal conditions for the growth of coral reefs. Sea levels were high, and vast, shallow seas flooded the edges of the continents, forming gigantic shelf zones literally teeming with life. The planet's atmosphere continued to rapidly become oxygenated. Thanks to the vigorous photosynthesis of plants, which now covered large swathes of land, oxygen levels rose to 20–22%, almost approaching modern levels. Carbon dioxide in the air was still much higher than today, maintaining a powerful greenhouse effect and a warm climate. However, toward the end of the period, its concentration began to decline as plants actively absorbed it from the atmosphere, accumulating it as organic matter. The oceans of the Devonian period were a true kingdom of fish. Jawweeds, which appeared at the end of the Silurian, underwent an incredible evolutionary explosion in the Devonian. They diversified into numerous groups, each occupying its own ecological niche. Placoderms, or armored fishes, became the apex predators of the Devonian seas. Their massive bony armor, like the armor of a medieval knight, covered their heads and front parts, making them virtually invulnerable. Take a look at this monster, the ruler of the Devonian seas. Its name is Dunkleosteus, and it was one of the most fearsome representatives of the armored fishes or placoderms. It was not just a predator, but a true underwater fortress, an armored killing machine. Imagine a creature 6 to 10 meters long, comparable to a modern school bus, and weighing several tons. Its skull was encased in thick armor, made of fused bony plates. But the most terrifying thing lurked in its mouth. Dunkleosteus had no teeth as we know them. Instead, nature armed it with monstrous bony plates honed to the sharpness of guillotine blades. These deadly edges constantly rubbed against each other, remaining perfectly sharp throughout its life. With a single swipe of its jaws, it could easily crush the shell of another fish or crack the tough shell of an ammonite like a nut. This apex predator knew no equal in its ecosystem. Dunkleosteus was the absolute king, patrolling the waters and mercilessly destroying anything unwary enough to cross its path. Of course, not all placoderms reached such titanic proportions. Among them were much more modest, but no less astonishing creatures. Take, for example, Bothrialepis, a seafloor dweller clad in armor from head to tail. Its powerful pincers were capable of grasping and crushing unwary prey, and its tail was tipped with a venomous sting that paralyzed its victims. Pulmonoscorpius was one of the first arachnids to fully adapt to life on land, breathing atmospheric air using primitive lung sacs. The insect world of that era was incredibly rich. It was then that the first cockroaches appeared, some of which grew up to 10 centimeters. True giants by today's standards. They scurried about in the forest litter, serving as important sanitation workers. The air was filled with the chirping of primitive orthopterans, the ancestors of modern grasshoppers and crickets. Some of them had already learned to produce sounds by flapping their wings, and these first timid trills became the soundtrack of the coal forests, breaking the silence previously interrupted only by the rustling wind. Life was also thriving in the water. Sharks continued to evolve, producing ever more bizarre and specialized forms. For example, Stethecanthus possessed an absolutely incredible dorsal fin, reminiscent of a brush on an anvil and covered in tiny teeth. Scientists still debate the purpose of this strange structure. Perhaps it served for mating or to ward off larger predators. And the jaw of another shark, Helicoprion, concealed a true marvel of natural engineering. Its teeth didn't fall out, but rather spiraled inward as they grew, forming a perfect spiral of teeth, reminiscent of a circular saw. Its front fins had evolved into hard limb-like appendages, which it used like an excavator to dig through the bottom sediments in search of food. Its relatives, known as antiarchs, were also small armored fishes that peacefully fed on organic remains and small invertebrates. And Philolepis, with its perfectly flat body, allowed it to masterfully camouflage itself, almost completely burying itself in the sand on the seabed. However, not all inhabitants of the Devonian seas relied on heavy armor. Acanthodians, often called spiny sharks, adopted a completely different survival strategy and continued to thrive. These small and agile fish were covered in tiny scales, and a needle-sharp spine protruded from the front of each fin. Instead of brute strength and impenetrable armor, Acanthodians relied on speed and maneuverability, gathering in schools to hunt small fish and invertebrates. At the same time, cartilaginous fishes, the ancestors of modern sharks, rays, and chimeras, emerged. Appearing in the Devonian period, they quickly occupied their niche in marine ecosystems. The first sharks were by no means giants. Their lengths rarely exceeded 1 meter, but their anatomy already showed all the traits of future rulers of the ocean. A streamlined, torpedo-shaped body, powerful jaws with the rows of sharp teeth, and a phenomenal sense of smell. Cladocelache, one of these early sharks, possessed broad pectoral fins and a strong tail, making it an incredibly fast and agile hunter. Its teeth, each with 3 cusps, were ideal for holding slippery and elusive prey. It was in the Devonian that the ray-finned fishes, a group that today comprises the vast majority of all fish on the planet, emerged. Their key feature was fins supported by a network of thin, bony rays. This design provided them with unrivaled flexibility and precision in their movements through the water. One of the pioneers of this group was Cheirolepis, a small silvery creature that fed on plankton and other small aquatic organisms. Ray-finned fishes did not yet play a major role in the Devonian seas, but this was merely the calm before the storm. They were destined to become the most successful and numerous group of vertebrates in the world's oceans. But the most important characters in our story are the lobe-finned fishes. Look at their fins. They don't resemble the thin fans of ray-finned fishes. They are fleshy, powerful appendages, concealing a bony skeleton strikingly reminiscent of the limb structure of land animals. The lobe-finned fishes of that time were divided into several lineages. Coelacanths were leisurely predators of the deep, protected by scales as tough as chainmail. Another group, the lungfishes, or lungfishes, colonized freshwater bodies. They made an incredible evolutionary breakthrough. They learned to breathe atmospheric air using primitive lungs. This skill allowed them to survive the most difficult times, when their lakes and rivers dried up during droughts. One of the most striking representatives of the lobe-finned family was Eusthenopteron, a fairly large predator, approximately 1.5 meters long. Its powerful muscular fins were so strong that it could use them to propel itself along the bottom of shallow, overgrown swamps. Imagine this scene: murky water, dense thickets of aquatic plants, fallen tree trunks, and amid all this chaos, Eusthenopteron darts forward, hunting for unsuspecting prey. Its jaws were lined with sharp teeth, and its nostrils connected to its mouth. This allowed it to stick the tip of its snout out of the water and gulp air without surfacing entirely. It was from the descendants of such creatures that the first land-dwelling creatures emerged. Let's fast forward to the middle of the Devonian period, approximately 385 million years ago. At this point, some lobe-finned fishes began to do the unthinkable. They decided to abandon the water. What prompted them to take this desperate step? Perhaps a severe drought was drying up their native waters, forcing them to crawl into neighboring ponds to survive. Or perhaps the land lured them with its safety. There were no large predators there yet. Or perhaps they were drawn by the abundance of food. The shores literally teemed with invertebrates, making them easy and nutritious prey. And here we have a creature that has become a true sensation in paleontology. Its remains were found in late Devonian deposits in what is now Canada. They were still slaves to the water, emerging on land only for short periods. These pioneers inhabited marshy coastal areas where land and water intertwined. Here, they hunted the first land invertebrates, millipedes, scorpions, and primitive insects that had already colonized the continents. They entrusted their offspring only to water. The eggs were laid in ponds, and the larvae were completely aquatic, breathing through gills and swimming with their tails. Only after they had matured were they given the chance to set foot on solid ground. This great vertebrate emergence onto land was only possible thanks to another no less monumental event: the revolution in the plant kingdom. During the Devonian period, plants made an incredible evolutionary leap. From the low, primitive forms of the Silurian period, they transformed into mighty trees. Archaeopteris, one of the first tree-like plants, soared into the sky to heights of up to 30 meters. Its mighty trunk was covered in bark, and fern-like fronds hung from its branches. Although Archaeopteris reproduced by spores like a fern, its wood was truly woody, with annual rings that signaled the changing seasons. These plants, called progymnosperms, were a transitional link between ferns and seed plants. By the end of the Devonian, the first true seed plants appeared. The invention of the seed was an event for the plant world comparable to the invention of the wheel for humanity. The seed contained a reserve of nutrients for the embryo and was protected by a tough seed coat, allowing plants to disperse and reproduce far from water sources. The tree-like club mosses of the Devonian also reached impressive proportions. Lepidodendron and its relatives grew to heights of 30 to 40 meters, forming the first true forests in Earth's history. These were strange trees, a straight, unbranched trunk covered with diamond-shaped scars from fallen leaves and a lush crown of long, narrow leaves at the very top. Horsetails were not far behind either, calamites reached 10 to 15 meters in height and formed dense, impenetrable thickets on the marshy banks. By the end of the Devonian period, the continents were clothed in a verdant mantle of vast forest. But let's cast aside familiar images. The forests of the Devonian period were a world of silence and strange forms, completely alien to our perception. There were no flowers, no grass, no birdsong, only bare tree trunks soaring skyward, the rustle of the wind in their crowns, and beneath our feet a carpet of ferns and primitive club mosses. The forest floor consisted of fallen leaves, rotting tree trunks, mosses, and lichens. These first forests radically changed the face of the entire planet. Plants, like giant pumps, began sucking enormous amounts of carbon dioxide out of the atmosphere, sequestering it in their wood and leaves. When the trees died, some of this carbon became trapped in the soil, unable to return to the atmosphere. This triggered a global process. CO2 levels began to steadily decline, leading to a gradual cooling of the climate. Plant roots, penetrating deep into the soil, accelerated the disintegration of rocks, and torrents of rainwater washed tons of minerals into the oceans. This flood of minerals, gushing from the land, became a deadly poison for the oceans. The excess nutrients triggered an explosive growth of algae. The oceans literally bloomed. As these giant masses of algae died, their decomposition consumed colossal amounts of oxygen. Vast oxygen-free dead zones began to form in the oceans. These zones expanded, suffocating all life in their path: fish, invertebrates, especially those living on the seabed. Added to this was global cooling caused by falling carbon dioxide levels. By the end of the Devonian, average global temperatures began to decline. Ice caps began to grow in the high latitudes of the supercontinent Gondwana. The water trapped within these glaciers led to a sharp drop in sea levels. Vast shallow seas, which had been a cradle for an incredible diversity of life, began to retreat, exposing the ocean floor. All these changes triggered a series of mass extinctions that stretched over the last 25 million years of the Devonian period. This was not a single catastrophe, but a series of fatal blows, each wiping out a significant portion of species. The builders of underwater cities, coral reefs, were particularly hard hit. The tabulate and rugosa corals, which had spent centuries building their limestone towers, were almost completely destroyed. The Devonian world, once teeming with life, sank into silence. Great reef ecosystems, these underwater megacities built over millions of years, simply collapsed. Along with them, thousands upon thousands of species whose existence was inextricably linked to these coral labyrinths sank into the abyss of oblivion. Trilobites, ancient sea creatures whose numbers were already declining, suffered a crushing blow. Entire families were wiped from the face of the earth forever. Even the most formidable predators couldn't resist. The splacoderms, the armored rulers of the Devonian oceans, didn't survive to the end of this era. Their reign was over. Every single species of these armored fish died out, leaving the throne free for new rulers of the deep, faster and more advanced sharks and bony fish. Brachiopods, similar in appearance to mollusks, also suffered colossal losses, although some groups miraculously managed to survive. What caused this global catastrophe, this Devonian mass extinction? Scientists have no single answer. It was likely a chain of tragic events. A sharp drop in sea levels literally dried up coastal shallows, depriving countless species of their natural habitats. At the same time, oxygen levels in the water plummeted, leading to the death of all bottom-dwelling species. Global cooling dealt a fatal blow to tropical species adapted exclusively to warm waters. Volcanoes may have also played a role, erupting and spewing millions of tons of ash and toxic gases into the atmosphere. Some researchers even speculate that the final straw may have been an asteroid impact, which exacerbated the already dire situation, although no compelling evidence has yet been found for this theory. But while the oceans were turning into dead zones, a completely different picture was unfolding on land. Here, life wasn't just surviving, it was thriving. Forests continued their triumphant march, capturing ever-new territories across the continents. Arthropods explored uncharted ecological niches, giving rise to ever more bizarre forms. It was then that the first winged insects appeared in the air, although their true moment of glory would come a little later, in the following Carboniferous period. The millipedes in these forests reached truly monstrous sizes. Imagine Arthropleura, a giant centipede that grew up to 2.5 meters in length during the late Devonian and early Carboniferous periods. This living armored train slowly crawled along the forest floor, crushing rotting leaves and wood with its jaws. Its segmented body was reliably protected by a tough shell, which protected it from its few predators. Spiders and scorpions also emerged onto land to stake their claim. Ancient scorpions were large creatures, some reaching 70 centimeters in length, armed with powerful pincers and a venomous stinger on their tails. Some still led a semi-aquatic lifestyle, stalking prey in the shallows of swamps, but others had already fully transitioned to land, becoming some of the first truly terrestrial hunters. Meanwhile, spiders began weaving their first webs. Of course, these weren't the complex trapping structures we see today. They were likely simple silken sheets, used to line their burrows or wrap egg clutches. But even without hunting webs, spiders were already active and dangerous predators, stalking and attacking small insects and other arthropods. The forest floor was teeming with its own life, invisible to the eye. Ticks and primitive insects swarmed through the fallen leaves, feeding on decaying organic matter, spores, and fungi. They formed the foundation of the first terrestrial food chains. They were preyed upon by predatory arthropods, which in turn were preyed upon by larger predators, such as scorpions and giant centipedes. Food webs became increasingly complex and tangled. The fresh water of the Devonian period was also teeming with life. Rivers and lakes were teeming with fish, lobe-finned fish, ray-finned fish, and even the last of the armored species swam here. Invertebrates, mollusks, crustaceans, insect larvae occupied every available niche. Bony fish dominated both fresh and salt waters. Ray-finned fish flourished, exploiting every available ecological niche. It was then that the first distant relatives of modern sturgeons, catfish, and pike appeared. The seas teemed with ammonoids, cephalopods with spiral shells. Their diversity was astonishing, from tiny forms the size of a coin to veritable giants with shells a meter in diameter. Crinoids, or sea lilies, reached the peak of their power in the Carboniferous period, In some regions, they formed such dense underwater forests that literally every centimeter of the seafloor was occupied by their stems. Entire layers of crinoid limestone formed from their remains. But the most revolutionary events of that era unfolded on land. Vertebrates continued their great march to conquer the continents. Amphibians, descendants of the Devonian lobe-finned fishes, achieved incredible diversity. Among them were tiny creatures similar to modern salamanders and true giants several meters long. A typical representative of the large amphibians was Eriops, a 2-meter-long creature with a massive body, a broad, flat head, and short but powerful legs. Eriops spent most of its life in or near the water's edge, ambushed by fish and other smaller amphibians. Its mouth was lined with sharp teeth, ideal for holding slippery prey. The skin of Eriops, like that of all amphibians, required constant moisture which forever tied it to bodies of water. Aquatic plants covered the shallows in a dense carpet, providing shelter for fry and small animals. By the end of the Devonian period, approximately 359 million years ago, our planet had changed beyond recognition. The continents were covered in dense green forests. Vertebrates took their first tentative steps onto land and began to explore this new world full of dangers and opportunities. Armored placoderms disappeared from the oceans, but their place was immediately taken by sharks and bony fish, which began to thrive. Coral reefs lay in ruins, but life, as always, stubbornly forged its way forward. The Devonian period was a time of incredible triumphs and horrific tragedies. Fish reached the peak of their diversity, but then many of their groups were wiped out. Plants conquered the land, creating the planet's first forests, but their very success triggered climate change that led to the mass extinction of life in the oceans. Vertebrates emerged onto land, opening a new chapter in evolutionary history. But the oceans paid a terrible price. The age of fishes ended in global catastrophe, but the seeds of the future had already been sown. The tetrapods that emerged at the very end of the Devonian would become the ancestors of all land vertebrates, amphibians, reptiles, mammals, and even birds. And the forests that blanketed the continents would continue to grow and change, creating ever more complex and wondrous ecosystems. And although many of the majestic creatures of the Devonian period disappeared from the face of the earth forever, new life forms were ready to take their place, playing the next act in the great drama of evolution. 359 million years ago, the planet entered one of the greenest eras in its entire history. The Carboniferous period had arrived, and it got its name for a reason. It was during this time that gigantic coal deposits formed deep within the earth, deposits that humanity would mine hundreds of millions of years later. This was an era when the continents were covered with unprecedented forests, when insects the size of modern seagulls soared through the air, and the first vertebrates, having completely severed their connection to water, roamed the land. Scientists divide the Carboniferous period in two parts: the early, or Mississippian, which lasted from 359 to 323 million years ago, and the late, or Pennsylvanian, which lasted from 323 to 299 million years ago. Each of these eras was unique in its own way. At this time, the continents continued their slow movement toward each other, preparing to merge into a new supercontinent. Laurussia, which had formed in the Devonian, was now approaching the enormous southern Gondwana. Their collision would give rise to entire mountain ranges: the Appalachian Mountains in North America, the mountains in Europe, and the Ural Mountains in Asia. By the end of the period, these land masses would merge into a single giant continent, Pangaea. But for now, oceans and shallow, warm seas still stretched between them. The climate at the beginning of the Carboniferous period was extremely warm and humid. Equatorial regions were literally drenched in tropical rainfall, creating ideal conditions for the growth of giant swamp forests. Sea levels were high, and vast lowlands were either inundated by shallow seas or transformed into vast swamps. But towards the end of the period, the climate began to change. The formation of Pangaea resulted in vast interior regions of the continent becoming cut off from the oceans. This led to their gradual drying and the emergence of a seasonal climate, with wet periods alternating with dry ones. But the most striking feature of this era was the air itself. The Carboniferous atmosphere was supersaturated with oxygen, reaching concentrations unseen before or since in the history of the planet. Vast forests, acting like giant lungs, pumped up to 35% oxygen into the atmosphere, almost 2/3 more than we breathe today. This oxygen-rich environment had dramatic consequences for life. Arthropods, whose respiration was limited to a primitive system of tracheal tubes, were able to grow to incredible, gigantic sizes. And fire became a far more terrifying and destructive force. Forest fires ignited from the slightest spark or lightning strike and raged with unprecedented ferocity, devouring everything in their path. The Carboniferous forests themselves were completely different from those of today. The trees that dominated these ecosystems belonged to groups that are now either extinct or represented by humble grasses and small plants. Giant lycopods, club mosses, towered up to 45 meters into the sky. The lepidodendron, or scale tree, had a straight columnar trunk that reached 2 meters in diameter at the base. Its trunk was covered in a distinctive diamond-shaped pattern, the scars left by fallen leaves giving the tree the appearance of giant pineapple or snake scales. At the top of this giant tree was a crown of long, narrow, grass-like leaves. These leaves continually grew and fell, leaving those characteristic scars on the trunk. The lepidodendron's root system was shallow but very spreading. Massive rhizomes, which scientists call stigmaria, extended from the base of the trunk in all directions, anchoring the tree in the marshy, unstable soil. Sigillaria, a close relative of lepidodendron, was similar in structure, but its trunk was not smooth, but ribbed with vertical grooves. Both of these groups of trees reproduced by spores, which matured in huge cone-like structures at the treetops. When the spores matured, the cones split open, and millions of microscopic spores were carried by the wind, settling on the moist soil of the swamps. Calamites, giant horsetails, also played an important role in these forests. These trees reached 20-30 meters in height and had hollow, segmented trunks with whorls of thin branches extending from each node. Calamites grew in dense thickets along riverbanks and in swamps. Their rhizomes intertwined underwater, creating entire colonies. The lower layers of the forest were filled with ferns. Some were tree-like and reached 10 to 15 meters in height. For example, Ceronius, one such tree-like fern, had a thick trunk that was actually composed of tightly intertwined aerial roots. These supported a palm-like crown of enormous feathery fronds, and beneath the canopy of these giants lay a dense green carpet of smaller ferns. Seed ferns, or pteridosperms, were another important group of plants of the time. They did indeed resemble ferns in appearance, but they reproduced by seeds rather than spores, a huge evolutionary step forward. Plants such as Medulosa and Neuropteris had woody stems and large pinnate leaves. Their seeds were quite large, surrounded by a fleshy coat, which may have attracted ancient animals that helped disperse them. Toward the end of the Carboniferous period, the first true conifers emerged. Chordates were tall trees with straight trunks and long, narrow leaves that grew spirally. They already produced cones with seeds and were much more tolerant of drought conditions. Nearby lived Diplovertebron, a smaller amphibian resembling a modern salamander. It preferred to hunt insects and other invertebrates on the forest floor. Its streamlined body and long tail allowed it to swim well and move quickly on land, but it always stayed in damp, shady places. However, the greatest evolutionary breakthrough of the Carboniferous period was the emergence of amniotes, vertebrates that learned to lay eggs directly on land. This was a revolutionary invention. Until then, all tetrapods were slaves to the water. To reproduce, they needed to return to their native element. Their eggs and larvae could only develop in a moist environment. The amniotic egg changed the game forever. It was enclosed in a strong protective shell that prevented it from drying out. Within this personal incubator was an entire life support system. The amnion created a fluid environment for the embryo, the allantois served to collect waste, and the yolk sac provided all the necessary nutrients. Now the young could fully develop inside the egg and hatch as a miniature version of the adult animal. This gave amniotes freedom. They were no longer tied to water to reproduce. One of the oldest known amniotes is Hylonomus, a small, agile creature about 20 centimeters long. Its remains were found in a surprising place, inside the petrified stumps of ancient trees in Nova Scotia. These tiny animals likely hid there from predators or the elements, but sometimes the trunk became a deadly trap. Hylonomus had a scaled body, a long tail, and slender legs. It was an active hunter of insects and other small invertebrates. The advent of the amniotic egg paved the way for vertebrates to achieve complete dominance on land. They could now inhabit the arid interior regions of continents, inaccessible to amphibians. Soon, amniotes diverged into two great evolutionary lineages. The first were the synapsids, a lineage that would, in the distant future, give rise to mammals. The second were the sauropsids, the ancestors of all reptiles and birds. The early synapsids of the Carboniferous period were still modest, lizard-like insectivores. One of them, Archaeothyris, about half a meter long, already possessed the key feature that distinguished all synapsids, a single opening in the skull behind the eye socket, the so-called temporal fenestra. These early synapsids were not yet dominant, but they laid the foundation for the group destined to become the rulers of the land in the following Permian period. Food chains on land became increasingly complex and intricate. At their base stood plants, giant club mosses, horsetails, and ferns. They fed on herbivorous arthropods, insects, and millipedes. These herbivores, in turn, were hunted by predatory arthropods, scorpions, spiders, and predatory insects. Small amphibians and early reptiles ate the insects, which themselves became prey for larger amphibians. But this ecosystem differed strikingly from modern ones. There were virtually no large herbivorous vertebrates. All early amphibians and reptiles were predators. Plant matter remained inaccessible to them due to its high content of tough, indigestible substances, lignin, and cellulose. Only much later, in the Permian period, did specialized herbivorous vertebrates appear whose digestive systems could cope with such coarse food. Toward the end of the Carboniferous period, the planet's climate began to change again. The continents converging formed the gigantic supercontinent Pangaea, which stretched from pole to pole. The interior regions of this megacontinent were vastly separated from the oceans, and moist winds simply couldn't bring rain. Aridification, the drying of vast territories, began. The era of endless rainforests and coal swamps was coming to an end. They were gradually replaced by more arid landscapes, heralding the advent of a new world. The planet was changing, and these changes were irreversible. The decline in atmospheric carbon dioxide, that invisible heat blanket, triggered a chain reaction of global cooling. Imagine the giant continent of Gondwana, with ice beginning to form on its southern tip. At first timidly, then with increasing confidence, the ice caps, like a white plague, spread from the South Pole, paralyzing the Earth. The glaciers advanced inexorably, engulfing vast territories beneath their deathly mantle. The world was no longer perpetually warm and humid. The climate acquired sharp, seasonal characteristics. Periods of torrential rains alternated with parching droughts, and warm seasons gave way to severe cold. These changes dealt a fatal blow to the plant kingdom. The majestic, moisture-loving forests of giant club mosses and horsetails, which for centuries dominated the swampy lowlands of the early and middle Carboniferous, began their long journey to extinction. Their era was drawing to an end. New, more resilient fighters had taken their place: seed ferns, cardates, and the very first conifers. These were the ones prepared for the harsh future. The endless swamps, those coal factories, were drying up, and with them, the source of the Carboniferous period's greatest wealth was drying up. By the end of the Carboniferous period, coal accumulation had virtually ceased. The animal world found itself at a crossroads. Dark times had arrived for many amphibian species whose lives were inextricably linked to water and swampy bogs. Their familiar world was disappearing before their eyes, shrinking with each drying swamp. But where some lost, others gained an opportunity. And the amniotes seized this opportunity, creatures that, thanks to their unique egg, were able to break the shackles of the aquatic element, found themselves in an advantageous position. They began rapidly colonizing new, drier regions of the sprawling Pangaea, diversifying and occupying empty niches. Even the insect world wasn't immune. Species emerged whose bodies were better protected from the scorching heat. But nature's most ingenious invention lay ahead. Some groups of insects mastered complete metamorphosis, a life cycle that included a magical transformation. A larva living its life would pupae, only to be reborn as an entirely different adult. It was a brilliant move. Larvae and adults no longer competed for food and territory. Toward the end of the Carboniferous period, approximately 299 million years ago, Earth was preparing for new, even more dramatic upheavals. the supercontinent Pangaea had almost completely closed its embrace, uniting virtually all of the planet's landmass into a single gigantic mass. The climate became increasingly harsh and contrasting. Glaciers were advancing in the south, while the equatorial regions remained immersed in warmth and moisture. Sea levels fluctuated constantly, rising and falling in sync with the growth and melting of ice sheets. The Carboniferous period was an era of incredible breakthroughs. It was then that plants formed the planet's first true forests, forever changing the atmosphere and climate. Arthropods, exploiting the oxygen-rich air, reached monstrous sizes, and vertebrates finally conquered land, inventing the amniotic egg, the key that allowed them to break free from their aquatic cradle forever. Food chains became more complex, becoming multi-layered and intricate. But this wondrous green world, a world of swampy forests and giant insects, was doomed. Climate upheavals caused by the birth of Pangaea and the fall in carbon dioxide levels were already reshaping the world map. In the next Permian period, these changes would reach their climax and lead to one of the most devastating mass extinctions in the history of our planet. But before the catastrophe, life would experience its last great flowering, giving birth to amazing and bizarre forms, many of which would perish forever, leaving no descendants. We stand on the threshold of a new era, approximately 299 million years ago. Earth is entering the Permian period, a time of incredible contrasts, an era that will be the scene of both the greatest triumph of terrestrial life and the most horrific catastrophe our planet has ever seen. It will be a time of extremes, from lush, thriving ecosystems to near-scorched ruins. This will be the era when synapsids, our distant ancestors, the harbingers of mammals, reigned supreme on land, when the first true coniferous forests arose and climate swings swung to unprecedented proportions. At the center of all this was the gigantic supercontinent Pangaea. By the beginning of the Permian period, it had almost completed its formation, drawing together almost all of the planet's land mass into a single colossal massif, stretching from pole to pole. To the north lay the lands that would become North America, Europe, and Asia. To the south lay a single block comprising the future Africa, South America, Antarctica, Australia, and India. Between these two parts, the ancient Tethys Ocean jutted like a gigantic wedge, while to the west, the supercontinent was washed by the boundless waters of the Panthalassa Ocean, which covered more than half the globe. This geography had truly dramatic consequences for the climate. The vast north-south landmass created extreme climate zones. Imagine the interior regions of this megacontinent, thousands of kilometers from the oceans. Moist winds simply couldn't reach them. As a result, vast, lifeless deserts and semi-deserts spread out in the heart of Pangaea. Coastal areas remained wetter, but even here the climate became sharply seasonal, with alternating rainy and dry seasons. At the South Pole, in the lands of Gondwana, the Great Ice Age, which had begun at the end of the Carboniferous period, continued. Massive ice sheets covered the territories of what would become Antarctica, Southern Africa, South America, and Australia. This glaciation affected the entire planet, lowering sea levels and generating cold currents that rushed northward. However, by the middle of the Permian period, the icy grip began to weaken, and the world gradually began to warm. The atmosphere of the early Permian was still rich in oxygen, although its level had begun to decline from its peak of 35% during the Carboniferous period. By the end of the era, oxygen content had plummeted to 15 to 16%, even lower than modern levels. Simultaneously, carbon dioxide concentrations began to rise, especially toward the end of the period, when monstrous volcanic activity released enormous volumes of it into the atmosphere. This triggered a powerful greenhouse effect and led to abrupt global warming. The flora of the Permian period was strikingly different from what we saw in the Carboniferous swamps. The moisture-loving giants, club mosses, and horsetails virtually disappeared along with their swampy homes. Their place was taken by new, much more drought-resistant plants. Conifers came to the fore, becoming the dominant force in many ecosystems. Early conifers, such as Walchia and Voltsia, had needle-like leaves covered in a waxy coating that helped retain precious moisture. They formed forests that are already somewhat reminiscent of today's taiga forests. Seed ferns, particularly glossopterids, dominated the southern regions of Gondwana. Glossopteris was a medium-sized tree with distinctive tongue-shaped leaves. These plants were ideally adapted to the cold climate of high latitudes and formed vast forests, even at the edges of ice sheets. Their fossils are found today throughout South America, Africa, Antarctica, Australia, and India, providing some of the strongest evidence for the existence of a single continent, Gondwana. During the Permian, ginkgos, trees with distinctive fan-shaped leaves that favored the temperate climate of river valleys and coastal areas, emerged and spread rapidly. Cycads, palm-like plants with thick trunks and crowns of feathery leaves, also became an important part of the landscape. They were even more drought-resistant. Ferns, of course, remained, but they lost their dominant position, huddling in damp lowlands, along riverbanks, and on shaded slopes. Horsetails and club mosses were reduced to small herbaceous forms, and mosses and lichens covered rocks and tree trunks, creating green oases in arid landscapes. The Permian forests were different, lighter and more sparse than the dark thickets of the Carboniferous. There was more space between the trees, and sunlight penetrated freely to the ground, creating conditions for the development of a diverse undergrowth. But it's important to remember that in many regions of Pangaea, there were no forests at all, only endless deserts with sparse, thorny vegetation or bare rocks. The animal world of this era was astonishingly diverse. On land, synapsids dominated, a group of amniotes to which we, mammals, ultimately belong. Early Permian synapsids belonged to the pelycosaur group. Many of them possessed a striking feature, a huge dorsal sail made of elongated vertebral processes covered in skin. And among these early rulers of the world, one stood out, whose name became synonymous with the Permian predator, Dimetrodon. It wasn't a dinosaur, but one of the most famous pelycosaurs. A true killing machine, it reached 4.5 meters in length. Its massive body was crowned by a huge head with jaws capable of crushing bone, but the real secret of its success lay in its mouth. Unlike most reptiles with their uniform teeth, Dimetrodons were varied. Huge fangs for piercing flesh and smaller, sharper teeth for slicing prey. This was a revolutionary innovation, allowing it to butcher its prey with unprecedented efficiency. But its most striking feature was, of course, its enormous dorsal sail, laced with blood vessels. Scientists see this sail as a brilliant piece of engineering, a personal thermostat. Imagine a cold morning. Dimetrodon turns sideways to the first rays of the sun, and its sail acts like a solar battery, quickly warming its blood and distributing the heat throughout its body. And when it became too hot at midday, the sail transformed into a radiator, dissipating excess heat. This gave Dimetrodon a colossal advantage over other animals, allowing it to wake up faster in the morning and stay active longer. Its relative, Ediacaran, also sported a dorsal sail but was a staunch vegetarian. Its teeth were blunt and ideal for grinding tough plant matter. Ediacaran was one of the first truly large vertebrate herbivores, growing to 3 to 4 meters in length. It fed on coarse leaves, twigs, and possibly even algae in coastal lagoons. Its digestive system must have been incredibly complex to extract nutrients from such food. To survive, it had to digest tough cellulose, a difficult task most likely assisted by colonies of symbiotic bacteria living in its digestive system. Let's travel to the shores of ancient rivers and lakes where another astonishing inhabitant of that time awaits us, Ophiocodon. Imagine a creature straight out of the darkest legends, a semi-aquatic synapsid whose appearance was strikingly reminiscent of modern crocodiles. Its elongated, narrow mouth was studded with needle-sharp teeth, the perfect tool for capturing slippery prey in murky waters. Ophiocodon spent most of its life in the water, mercilessly hunting fish and unwary amphibians. Only occasionally did it emerge onto dry land to rest in the Permian sun and, perhaps, procreate. But time passed, and by the middle of the Permian, the age of pelycosaurs had come to an end. They began to disappear, giving way to a new, more advanced group of synapsids, the therapsids, which scientists often refer to as mammal-like reptiles. These new rulers of the planet were far more advanced creatures in many ways. Their skulls had acquired a more complex structure, and an enlarged temporal fenestra allowed for the attachment of incredibly powerful jaw muscles. Therapsids' teeth became even more specialized. The front incisors were used for biting, the sharp canines for piercing prey, and the molars for thoroughly grinding food. But most importantly, their limbs were now positioned not at the sides of the body, but almost vertically underneath it, making their gait and running much faster and more efficient. At the top of this brutal food chain reigned the Gorgonopsians, the true tyrants of the late Permian period. Growing up to 3 to 4 meters tall, these creatures were the very embodiment of nightmare. Their main weapon were enormous, curved, saber-like fangs. With a single crushing bite, they tore through the flesh of their victims, inflicting wounds that left no chance of escape. One of the largest representatives of this group, Inostrancevia, was a true monster, weighing up to 300 kilograms. This predator was capable of challenging the largest herbivores of its era. Its skull was massive, its jaws incredibly powerful, and its body, scientists speculate, may already have been covered in short fur or hair-like structures, the first tentative steps toward the thermal insulation that would become the hallmark of mammals. In contrast to these terrifying predators, there existed the most prosperous group of herbivorous therapsids, the Dicynodonts. Their name translates as two-fanged, and it's entirely appropriate. The vast majority of these creatures indeed had only 2 fangs in the upper jaw, while the remaining teeth were gone, giving way to a powerful horny beak, similar to that of modern turtles. These animals exhibited a striking diversity of shapes and sizes, from tiny creatures no larger than a rat to true giants like Lystrosaurus, which was the size of a large pig. Decinodonts use their beaks to shear tough vegetation, then crush it with their powerful jaw muscles. In the late Permian, cynodonts emerged, the most advanced and evolutionarily sophisticated group of therapsids. They developed complex, multi-cusped molars, allowing them to chew food with incredible precision. A secondary bony palate developed in their skull, a unique partition separating the nasal passage from the oral cavity. This innovation allowed them to breathe and eat simultaneously, something unattainable for more primitive animals. Their legs stood almost completely vertical, and their bodies were likely covered in thick fur. Cynodonts became the evolutionary bridge between reptiles and mammals. It was from their ranks in the following Triassic period that the first true mammals would emerge. However, synapsids weren't the only masters of the Permian world. Sauropsids, or reptiles more broadly, also flourished. Among them, the parareptiles stood out, including pariasaurs, massive, clumsy herbivores whose skin was covered with bony knobs and lumps. Scutosaurus, one of the largest pariasaurs, reached 3 meters in length and could weigh as much as a ton. Its body resembled a barrel, its limbs were short and columnar, and its entire skin was covered in bony plates that served as reliable armor against predators. Diapsids, another key branch of reptiles, gave rise to several important evolutionary lineages. It was then that the first archosauromorphs appeared, the distant ancestors of the future kings of the planet, dinosaurs, pterosaurs, and crocodiles. True, in the Permian period, they were still quite small and unremarkable creatures. Nearby, small, lizard-like reptiles scurried about in the undergrowth, constantly hunting for insects. Amphibians held their ground, although most of their giant forms died out as the swamps shrank. Those that survived were primarily aquatic or semi-aquatic, finding refuge in rivers and lakes. Among them were the temnospondyls, a group of large amphibians that included predators like Eriops and semi-aquatic creatures like Mastodonsaurus, whose finest hour would come in the Triassic. The oceans of the Permian period were also teeming with life. Sharks continued to evolve, even though many of their ancient relatives had already disappeared. Bony fish reigned supreme in both fresh and salt waters. Ray-finned fish diversified into countless groups, occupying every conceivable ecological niche. But the most astonishing marine inhabitants of that era were the reptiles that decided to return to the ocean. Mesosaurs, Mesosaurus, were small aquatic reptiles, about a meter long, with long, slender jaws, lined with a dense array of needle-like teeth. They glided through fresh and brackish waters, hunting for small invertebrates and fish. Remarkably, Mesosaurus remains have been found in both South America and Africa, providing further compelling evidence that these continents were a single entity during the Permian period. Brachiopods remained abundant on the seafloor, although their former diversity had already begun to decline. They were gradually replaced by bivalves, which occupied the same ecological niches but did so much more efficiently. Ammonoids flourished in the water column. Their spiraling shells were decorated with intricate patterns. Sea lilies created entire underwater meadows, although their diversity also declined. The coral reefs of the Permian period were quite modest. The ancient tabulate corals had almost completely disappeared, and rugosa, or tetraorbital corals, were only occasionally encountered. Calcareous sponges and algae now formed the basis of reef structures, but these structures could not compare to the majestic reefs of the Devonian and Carboniferous periods. Toward the end of the Permian epoch, the planet seemed to be going mad. The climate became a scorching furnace. The Great Gondwanaland Ice Age was a distant memory. The last glaciers that had capped the South Pole had melted without a trace. The world was plunging into an era of unbearable heat. Temperatures soared to unimaginable levels, especially in the heart of Pangaea, where summers could reach 40 or even 50 degrees Celsius. Winters at high latitudes remained cold, but the polar ice caps were no longer a thing of the past. Droughts became commonplace. Vast, once thriving territories within the supercontinent turned into lifeless, sun-baked deserts. Vegetation survived only in rare oases along rivers and lakes. Animal life suffered from a horrific shortage of water and food. Ecosystems across the planet became incredibly fragile and vulnerable. And then disaster struck. Approximately 250 million years ago, at the turn of the Permian and Triassic periods, the most devastating mass extinction in the history of our planet occurred. This event, known as the Great Dying, was more than just a tragedy. It was an apocalypse, wiping out more than 90% of all marine species and about 70% of land vertebrates. It was a blow of such devastating force that life itself on the planet was brought within a hair's breadth of total and final extinction. What caused this global carnage? Scientists believe it was a deadly cocktail of several destructive factors, but the main cause, the trigger for the apocalypse, was most likely the Siberian Traps, one of the most monumental volcanic eruptions in Earth's history. In what is now Siberia, the gates of hell opened. Millions of cubic kilometers of molten basaltic lava gushed to the surface, engulfing an area the size of modern-day Europe. These eruptions lasted for hundreds of thousands of years, releasing colossal volumes of carbon dioxide, methane, sulfur dioxide, and other toxic compounds into the atmosphere. Carbon dioxide triggered a runaway greenhouse effect, causing dramatic global warming. Ocean temperatures soared by 8 to 10 degrees, and land temperatures became even hotter. This warming led to the melting of enormous reserves of methane hydrates, frozen compounds of methane in water stored at the ocean floor. The release of methane, an even more potent greenhouse gas, added fuel to the fire, triggering a catastrophic chain reaction of warming. At the same time, sulfur dioxide and volcanic ash in the atmosphere blocked out the sun, causing a short-term cooling and halting photosynthesis in plants. Sulfur compounds formed acid rain, poisoning the soil and water bodies. The oceans began to acidify, literally dissolving the shells and skeletons of marine life. Rising water temperatures led to a catastrophic drop in oxygen levels. Warm water simply can't hold as much dissolved oxygen as cold water. To make matters worse, the circulation of ocean currents was disrupted, leading to stagnation of deep waters. It was during this era that the first large multicellular organisms in history emerged onto the scene, and these were incredibly strange, mysterious creatures, unlike anything living on modern Earth. Let's dive into the warm, calm waters of the Ediacaran Sea. Imagine standing on a sandy bottom. The water is crystal clear, and the sun's rays penetrating the depths create a soft, diffused light. And here on the bottom, you see something astonishing. These are not algae, not rocks, not corals. These are living creatures. But what creatures? They resemble flat discs, intricate feathers, quilts, or the imprints of giant fern fronds. Some of them lie on the bottom like living carpets. Others sway on short stalks. They are absolutely motionless, silent and mysterious inhabitants of the dawn of time. One of the most famous creatures of this era is named Dickinsonia. It was a flat, oval organism that could grow up to a meter in length, a veritable living carpet sprawled across the seafloor. Its body was divided into numerous segments that radiated from the center, resembling a giant leaf. Dickinsonia slowly crawled along the bacterial mat-covered seafloor, absorbing nutrients with its entire undersurface. It had no mouth, no eyes, and no digestive system. This creature was so primitive and yet so alien that paleontologists still fiercely debate its exact nature. An early animal? A giant fungus? Ocean abysses turned into gigantic oxygen-free zones from which toxic hydrogen sulfide began to rise to the surface, poisoning the water and even coastal air. On land, the heat and drought reached their peak. Forests dried out and burst into flames, burning in gigantic fires. Rivers and lakes turned into dusty riverbeds. Animals perished from thirst, hunger, and suffocation from toxic gases. Food chains collapsed one after another as plants, the foundation of any ecosystem, could not survive in these hellish conditions. By geological standards, the extinction was lightning fast, perhaps only a few tens of thousands of years. But for living creatures, it was a long and painful agony. Ecosystems collapsed like a house of cards. The most vulnerable species disappeared first, followed by the more resilient ones. By the end of this catastrophe, only the most resilient organisms, capable of withstanding extreme temperatures, oxygen deficiency, and toxic environments, remained. In the oceans, coral reefs vanished without a trace. All rugose and tabulate corals became extinct. Trilobites, which had existed on Earth for nearly 300 million years and survived numerous mass extinctions, succumbed this time and disappeared forever. Most brachiopod species perished. Entire groups of ammonoids, sea lilies, and sea urchins were wiped off the face of the Earth. Vast classes of marine animals simply ceased to exist. On land, virtually all large vertebrates perished. The fearsome gorgonopsians disappeared completely. Most dicynodonts were wiped out, with only a few genera surviving. The armored pariasaurs became extinct. Numerous groups of reptiles and amphibians vanished into oblivion. Of the rich diversity of Permian synapsids, only a few survived, mostly small, inconspicuous forms. The recovery of life after the Permian-Triassic extinction took millions of years. Ecosystems were devastated to their very foundations, and it took an incredibly long time for even the most basic food chains to recover. Let's fast forward to a world that barely survived its apocalypse. For several agonizing millions of years after the Great Dying, Our planet was a nearly lifeless desert. Only a few surviving species, true evolutionary outcasts, timidly began their journey to recovery, slowly reproducing and colonizing the desolate territories. But the former diversity of life was nowhere to be seen. Yet just a moment ago, in geological terms during the Permian period, the planet was a paradise teeming with life. Synapsids, our distant mammal-like ancestors, flourished to an incredible degree, giving rise to a stunning diversity of forms, from fearsome saber-toothed predators to massive lumbering herbivores. Plant life conquered even the driest corners of the earth, creating entirely new, complex ecosystems. The oceans teemed with life, but all this splendor was wiped from the face of the earth by the greatest catastrophe in history. Drastic climate shifts and monstrous volcanic eruptions reduced this thriving world to ashes, destroying almost all life. And yet, even after such total destruction, life proved its incredible resilience. Like a phoenix, it was ready to rise from the ashes. The few species that survived the inferno ushered in a new era. From the ruins of the Permian extinction, a new world was destined to emerge, the world of the Triassic. This would be the era in which legendary dinosaurs would take their first steps. Tiny but tenacious mammals would emerge, and life would once again find a way to flourish. So, 252 million years ago, we stand before a devastated planet. The Permian Triassic extinction left behind a scorched earth where only the most resilient and undemanding organisms survived. Ecosystems were razed to the ground. Food chains that had been built over millions of years were torn to shreds, and the vast majority of species disappeared from the face of the earth forever. But the very nature of life contains an astonishing ability to recover even from the most devastating blows. The Triassic period was a time of this slow, painful rebirth, a time of bold evolutionary experiments and the emergence of entirely new groups of animals that were destined to change the face of the planet for the next 150 million years. At the beginning of the Triassic, all the land on the planet was still gathered into a single gigantic supercontinent, Pangaea, which stretched from pole to pole. Its outline resembled a gigantic letter C, its claws encircling the warm waters of the vast Tethys Ocean. And to the west, as far as the eye could see, stretched the boundless Panthalassa Ocean covering most of the globe. The interior of Pangaea was a kingdom of death, scorching, waterless deserts where rain was rare and temperatures soared to extreme levels. Imagine this world. The climate here wasn't just hot, it was merciless and unstable. The planet had still not recovered from the cataclysm it had endured. The atmosphere was literally poisoned by carbon dioxide, creating a greenhouse effect of unimaginable magnitude. Average temperatures were 6 to 10 degrees higher than today, and even at the poles, there was no hint of ice caps. The equatorial zones were so scorchingly hot that these areas were probably completely unsuitable for large vertebrates. During the day, animals had to seek refuge in the shade of rocks or deep burrows, and only at dusk did they risk venturing out to search for food. To top it all off, breathing on this world was difficult. Oxygen levels in the atmosphere dropped to a critical 15–16%. This created enormous difficulties for all living things, especially in high-altitude areas, limiting their distribution. Sea levels were quite low at the beginning of the period, but over time they began to rise. slowly flooding coastal plains and creating new habitats. The revival of life in such conditions was a painfully slow process. During the first million years of the Triassic, biodiversity remained depressingly low. Surviving species slowly increased their numbers and spread across the planet, but ecosystems remained primitive and incredibly fragile. Vast areas were virtually lifeless, endless deserts, where only rare oases along river valleys could support sparse flora and a small number of animals. The flora of the early Triassic was bleak and monotonous. The majestic forests of the Permian period were destroyed by the catastrophic fire, and their recovery took an eternity. The pioneers, colonizing the scorched lands, were the most undemanding organisms, lichens, mosses, and ferns, capable of surviving in the poorest soils. In the damp lowlands, ferns formed dense, impenetrable thickets, and their wind-dispersed spores allowed them to quickly conquer new territories. Lycopods, descendants of the giant tree-like club mosses of the Carboniferous period, were now small herbaceous plants covering the banks of rivers and lakes. Horsetails were also ubiquitous, but no longer reached their former gigantic size. Seed ferns slowly regenerated, but their diversity was severely limited. It wasn't until the mid-Triassic that the landscape began to change. True forests reappeared on the planet, and conifers played a dominant role. Araucarias, distant relatives of modern Chilean pines, grew in temperate latitudes, forming tall forests with dense canopies. Podosa meets, an extinct group of conifers similar in appearance to modern yews and cypresses, preferred drier regions. Their needle-like foliage was covered in a thick layer of wax to protect against evaporation. Ginkgo trees, which had appeared as early as the Permian, truly flourished in the Triassic. Their easily recognizable fan-shaped leaves and trunks, reaching 30 meters in height, became a familiar part of the landscape. Cycads, palm-like plants with thick trunks and crowns of long feathery leaves, were also widespread, especially in the tropics and subtropics. And by the end of the Triassic, Benetites emerged, an extinct group of plants resembling cycads, but more closely related to angiosperms. Their massive, cone-like reproductive organs sometimes resembled primitive flowers. It was the Benetites that would become an important part of Mesozoic ecosystems, providing food for future generations of herbivorous dinosaurs. The animal world of this era was truly strange. Numerous ecological niches left vacant by the extinction event were slowly filled by the descendants of the survivors. And the protagonist of this post-apocalyptic scene was Lystrosaurus. This creature, the size of a modern pig, became a true king of survival. Its fossils have been found literally everywhere on every continent that was part of Pangaea, from Antarctica to India. Lystrosaurus had a barrel-shaped body, short but powerful legs, and a horny beak with which it sheared tough vegetation. It preferred to stay near water, spending much time in rivers to escape the unbearable heat. Its dominance was unique. In healthy ecosystems, no single species makes up the overwhelming majority of all vertebrates. But in the devastated world of the Triassic, competition was reduced to zero, and Lystrosaurus was able to occupy many empty niches at once. Only with time, when life began to recover, did his dominance fade away. Another group of survivors were the cynodonts, the most advanced of the theropoda. These small creatures, resembling a weasel or a large shrew, were active predators and omnivores. They already possessed teeth divided into incisors, canines, and molars, a secondary bony palate that allowed them to breathe and chew simultaneously, and were most likely covered in fur. Cynodonts hunted insects, small reptiles, and were not averse to carrion. It was from their ranks that the first true mammals would emerge at the end of the Triassic. And in the rivers and lakes of the early Triassic, true monsters lurked. Temnospondyle amphibians were the top aquatic predators of their time. Mastodonsaurus was one of them, a monster 4 to 6 meters long with a huge flat head up to a meter wide. This giant, resembling a giant salamander, was the perfect ambush predator. It could lie motionless on the bottom for hours, blending in with it, only to then lunge with its powerful jaws to snatch any unsuspecting prey. Its diet included fish, other amphibians, and even small reptiles that unwary people came near the water. But the most important fateful events unfolded in another group of reptiles, the archosauromorphs. They were destined to give birth to the future rulers of the planet, dinosaurs, pterosaurs, crocodiles, and even birds. At the beginning of the Triassic, these animals were still small and unremarkable. Proterosuchus, one of the earliest representatives, was a predator about 2 meters long, resembling a large lizard with an elongated snout and sharp teeth. It hunted small prey and never missed an opportunity to feed on carrion. By the mid-Triassic, archosauromorphs had split into 2 key lineages. One of them gave rise to the Crurotarsi, a group that included the ancestors of crocodiles and many other amazing creatures. Triassic Crurotarsi were incredibly diverse. Among them were gigantic predators such as Postosuchus. This monster, reaching 6 meters in length, resembled a crocodile standing on tall, straight legs. Postosuchus was the apex predator of its ecosystem, a veritable walking nightmare, hunting large herbivorous reptiles and the first still lumbering dinosaurs. There were also herbivorous Crurotarsians, such as the Ediacaran. These animals were veritable living tanks, covered from head to tail in heavy armor made of bony plates, which reliably protected them from predators. Desmatosuchus, one of the largest Ediacarans, grew up to 5 meters in length and was armed with massive spikes protruding from its shoulders. It used its beak to cut down low-growing vegetation and also to dig up succulent roots and tubers from the ground. Some Crurotarsi even returned to the water. Phytosaurs were strikingly similar to modern crocodiles. The same long, narrow snout lined with sharp teeth, the same streamlined body, and a powerful tail for swimming. They hunted in rivers and coastal seawater, feeding primarily on fish. Some phytosaurs grew to 10 to 12 meters, becoming the largest aquatic predators of their time. Another branch of archosauromorphs gave rise to the Avamatatasalians, a group that included dinosaurs and flying lizards called pterosaurs. The first dinosaurs appeared on the planet in the mid-Triassic period, approximately 235 million years ago. They were small, agile, and at first glance completely unremarkable compared to the giant amphibians and armored reptiles of the time. Eoraptor, one of the oldest known dinosaurs, was a light bipedal predator no more than a meter long that hunted small animals. But it and its relatives shared one key advantage. Their limbs were positioned not along the sides of their bodies, as in most lizards, but directly underneath them. This seemingly insignificant detail gave them a huge advantage in speed and endurance. This was the first step toward future dominance. It was a body built for speed and deadly precision, giving it a distinct advantage over most of the clumsy reptiles of the era. And here's another early predator, Herrerasaurus. Imagine a larger creature, up to 3 or even 4 meters long, the size of a modern crocodile. This was no ordinary predator, but a true killing machine, a tireless hunter armed with jaws pierced by razor-sharp teeth and powerful forelimbs capable of grabbing and holding on to writhing prey. In the appearance of Herrerasaurus, we already see the prototype of the future kings of the prehistoric world, the great theropods. Look at its anatomy. It already stands firmly on 2 legs, its neck curves into a deadly S-shape, ready for a lightning-fast lunge, and its long, muscular tail serves as an ideal balancer for running. By the end of the Triassic period, this evolutionary tree began to branch out, giving rise to an incredible diversity of forms. The first Saurischians, the so-called lizard-hipped dinosaurs, appeared on the scene, and immediately evolution took 2 paths. One branch gave rise to the theropods, swift bipedal predators that would only become more terrifying with time. The other branch, the sauropodomorphs, chose a different path, one of gigantism and vegetarianism. It was from their ranks that the titans with incredibly long necks would later emerge. Simultaneously, a second great group emerged, the ornithischians, or bird-hipped dinosaurs. All of them, without exception, were herbivores. Or a representative of an entirely different extinct life form that left no descendants? Other bizarre creatures lived alongside Dickinsonia. Charnia resembled a sea pin, a long stalk with numerous lateral branches. It was attached to the seabed and was likely a filter feeder, filtering microscopic food particles from the water. Tribrachidium looked like a disc with 3 spiral ridges radiating from the center. Its lifestyle and purpose remain a complete mystery. Sprigina, another inhabitant of those seas, had an elongated, segmented body with a thickening at one end resembling a head. Some researchers see it as a distant ancestor of arthropods, but this is nothing more than one of many theories. All these creatures inhabited vast shallows, where sunlight easily reached the bottom, providing food for bacterial mats and algae. They lived in a world devoid of predators. Imagine an entire world without a single hunter. Their main task was simply to exist, to grow slowly and absorb nutrients from the environment. There were no deadly chases, no furious struggles for survival as we know it. It was a world of astonishing, almost unreal tranquility, where life was only taking its first tentative steps toward multicellularity. But not all inhabitants of this world were completely passive. For example, Kimberella may have been one of the first truly active creatures. A typical predator of that era was Colophysis. Light as a feather, swift as the wind, it reached a length of about 3 meters. This agile hunter preferred not to act alone. Colophysis flocked in packs, forming a coordinated squad of killers that could hunt down and tear apart any small prey with their sharp teeth and claws. And this isn't just speculation. Paleontologists have discovered entire cemeteries of Colophysis bones, mass graves that tell us eloquently these dinosaurs were social animals living and hunting together. But while some honed their hunting skills, others became the first giants. Plateosaurus was one of the pioneers of large herbivores, a true giant of its time, growing up to 10 meters in length. This sauropodomorph was versatile. It could move leisurely on all fours, but when necessary, it could rise up on its hind legs to reach the succulent foliage in the treetops. Its long neck acted like a crane, delivering food from heights inaccessible to others. However, don't think that dinosaurs ruled the world by the Triassic. Far from it. They were just one of many competing groups of reptiles and far from the most successful. For most of the Triassic, the planet was dominated by Crurotarsi, the ancestors of modern crocodiles, which were far more diverse and numerous. So what enabled dinosaurs to ultimately emerge victorious in this evolutionary race? The answer lies in their structure. Their unique anatomy was a key advantage. Their legs, positioned not on the sides like those of lizards, but directly underneath the body, made dinosaurs much more efficient runners. This gave them a colossal advantage in speed and, more importantly, endurance. Moreover, there is every reason to believe that the dinosaur's respiratory system, with its air sacs, like those of modern birds, was an order of magnitude more sophisticated. It allowed them to extract maximum oxygen from each breath, a critical skill in the oxygen-poor atmosphere of the Triassic. Some researchers go even further, suggesting that dinosaurs may have been warm-blooded, giving them a huge energy advantage over their cold-blooded competitors. Meanwhile, a drama of its own was unfolding in the skies. In the Triassic period, pterosaurs, the first flying reptiles, took to the skies. One of the earliest of these, Eudomorphodon, had a wingspan of about a meter. Its wings weren't feathers, but a huge leather membrane stretched between its body and an incredibly elongated fourth finger. Eudomorphodon was an aerial fisherman, hovering above the surface of the water and snatching fish in mid-flight. Its jaws were lined with a palisade of sharp teeth of varying sizes, the perfect tool for holding slippery, agile prey. The Triassic oceans were also undergoing their own revolution. Several groups of land reptiles simultaneously decided to return to the water, readapting to life at sea. The most successful of these returnees were the ichthyosaurs. These creatures were a living example of convergent evolution. Though not fish, they acquired a striking resemblance to modern dolphins, a streamlined body, a powerful dorsal fin, and a forked tail. Nature itself suggested the ideal shape for swift swimming. Among them were true leviathans, the gigantic ichthyosaur of the late Triassic, Shanosaurus, could reach a length of 21 meters, making it one of the largest marine reptiles of all time. Its size was comparable to that of modern sperm whales. This colossus likely hunted squid and large fish in the open ocean, diving deep in search of food. Another group of marine reptiles were the nothosaurs, more primitive creatures. With an elongated body, long neck, and flippers instead of legs, they led a semi-aquatic lifestyle, spending time both in the water and on land like modern seals. Their hunting grounds were coastal waters, where they stalked fish and cephalopods. There were also some truly bizarre creatures. Placodonts were unusual marine reptiles that specialized in eating mollusks. Their teeth evolved into wide, flat plates, ideal for cracking tough shells. Some of them eventually developed a thick shell, making them resemble sea turtles, although they were not related. The water column was also teeming with life. Fish continued to evolve. The first true bony fishes appeared, a group that today accounts for the vast majority of all fish on the planet. They were far more agile and effective predators than their ancestors. Sharks, having recovered from the great Permian extinction, once again plied the oceans, although their diversity was still inferior to that of the Paleozoic era. Ammonites, cephalopods that had been nearly wiped off the face of the earth, experienced a rebirth and once again filled the seas with their spiral shells. Slowly but surely, coral reefs also recovered. A new group of corals emerged, hexacorals, the very same ones that build reefs today. By the end of the Triassic period, the planet seemed to have completely healed from the wounds of the Great Extinction. Dense forests covered the continents, and herds of herbivorous dinosaurs and cynodonts grazed within them. Following in their wake were predators, theropods, and fearsome crurotarsi. Pterosaurs soared the skies, and ichthyosaurs reigned supreme in the oceans. But this reborn world was doomed. History was about to deal another crushing blow. Approximately 200 million years ago, a new mass extinction occurred, known as the Triassic-Jurassic, which wiped out up to 80% of all species on the planet. The causes of this catastrophe are not fully understood, but the leading theory points to monstrous volcanic activity. Pangaea, a single supercontinent, began to break apart. The Earth's crust cracked at the seams, and millions of cubic kilometers of molten lava gushed from gigantic fissures onto the surface. These eruptions released unimaginable quantities of carbon dioxide into the atmosphere, causing a severe greenhouse effect. The planet began to suffocate from the heat and the oceans from acidification. Toxic acid rain scorched the land and poisoned the water. For many living creatures, these rapid changes were a death sentence. Crurotarsi, the rulers of the Triassic land masses, were almost completely wiped out. Only the ancestors of crocodiles, who found refuge in rivers and swamps, managed to survive. Giant amphibians also became extinct. The oceans emptied. Many groups of marine reptiles disappeared forever. But in this hell, there were survivors. Dinosaurs survived the catastrophe with remarkable success. And when the dust settled, they discovered a changed world. Their main competitors, the Crurotarsi, had disappeared. Dinosaurs were faced with limitless opportunities, empty ecological niches just waiting for new owners. In the coming Jurassic, they would become absolute dominance, achieving incredible diversity and gigantic size. The Triassic was their birthplace, but the Jurassic would be their era of triumph. It was then, in the shadow of the coming giants, that the first mammals appeared. These tiny, shrew-like creatures, descended from cynodonts, were barely noticeable. They already had fur, were warm-blooded, and likely nursed their young. They led a nocturnal, secretive lifestyle, hiding from the enormous reptiles in burrows and crevices. Throughout the era of dinosaurs, they would remain in the shadows, but it was in these inconspicuous creatures that the future lay. It was they, the mammals, who would inherit the Earth after the dinosaurs disappeared. The Triassic period was a time of great restoration, bold evolutionary experiments, and the birth of new life forms. It began on a devastated, nearly dead planet and ended with the creation of thriving, complex ecosystems. Dinosaurs took their first tentative steps. Pterosaurs conquered the skies. Marine reptiles became masters of the oceans. The stage was set for the next act, the Jurassic period, the golden age of dinosaurs. The Jurassic period had arrived. It was a time when the Earth seemed to awaken from the long, feverish slumber of the Triassic. The world was transformed. It became warmer, wetter, and much greener. Life blossomed riotously in all its splendor. Where once there had been sun-scorched plains, now lay endless, dense forests of giant conifers, ferns, and cicadas. The humid, warm climate and oxygen-rich air created the perfect incubator for what would forever symbolize prehistory, the dinosaurs. It was during the Jurassic that they reached the peak of their power, giving rise to an incredible diversity of shapes and sizes. Some were light and swift as birds, others enormous, like living mountains, slowly and inexorably moving across the ancient landscapes. Let's travel back 170 million years and imagine a morning in the Jurassic period. Thick fog hangs over the primeval forest. The shrill cries of pterosaurs echo in the high treetops. And in a clearing, shaking off the drops of dew, a huge herd of Diplodocus slowly awakens to life. Their incredibly long necks, like living cranes, rise smoothly above the treetops, welcoming the new day to reach the lush crowns hidden high in the sky. But Diplodocus weren't the only colossi of this era. The Jurassic world revealed true titans to the planet, Brachiosaurus, whose incredible necks soared so high that it seemed they could peer beyond the clouds. Their massive mountain-like bodies were supported by legs that resembled mighty columns, and their total body length could reach 25 meters. As these living monuments moved through the ancient forests, the very earth rumbled and trembled under their weight. However, despite their truly terrifying appearance, they were utterly peaceful, herbivorous giants, whose entire life revolved around the eternal search for fresh green food. The diversity of predators was no less astounding. The Jurassic period became a bloody arena for some of the most ferocious and effective killers in Earth's history. Allosaurus, long, incredibly powerful and swift, rightfully occupied the throne of the apex predator. Its enormous teeth, curved backward like serrated daggers, were the perfect tool for tearing the flesh of its prey. These killing machines often formed packs, making them a truly deadly threat. Just imagine this scene: a pack of hungry Allosaurus encircling a young Diplodocus, their deafening roars, full of fury, echoing through the prehistoric forest. In such merciless battles, the fate of not just one animal was decided, but the future of an entire generation. But it wasn't only giants that shaped the appearance of the Jurassic planet. At the same time, smaller dinosaur species, nimble, agile, and fast, began to actively evolve across the Earth. They hid in dense fern thickets, hunting insects, fish, and other small creatures. These seemingly modest creatures were the direct ancestors of future birds. Their bodies were already covered in feathers, which, while not yet suitable for true flight, were excellent for retaining heat and for flamboyant mating displays. It was during the Jurassic that nature itself took the first but confident step toward creating the world we know today as the world of birds. The Jurassic skies belong not only to these proto-pterosaurs, but also to the true rulers of the skies, the pterosaurs. With enormous leathery wingspans that could exceed 10 meters, they soared silently over coastal lagoons, scouting for fish and unwary small animals from above. Their graceful, almost mythical silhouettes painted scenes in the sky that still captivate our imagination. Some were tiny, no larger than a modern sparrow, while others were veritable aerial leviathans. And all of them, large and small, together created the unique atmosphere of a vibrant, noisy, and bustling world. The seas of that distant era were filled with their own mysteries and wonders. The Jurassic oceans literally teemed with ichthyosaurs, Ichthyosaurus, swift marine predators whose body shape was strikingly reminiscent of modern dolphins. They pierced the water at incredible speed, pursuing schools of fish and squid. Plesiosaurs, Plesiosaurus, glided majestically alongside them with their incredibly long necks and powerful flippers, allowing them to gracefully maneuver through the depths. And in the open ocean, Pliosaurus reigned supreme, massive sea monsters whose bite is rightfully considered one of the most powerful in the history of the planet. All these amazing creatures lived in a fragile yet astonishing balance. Jurassic Earth resembled a gigantic living organism where every detail had a purpose. Vegetation grew in incredible abundance, providing food for the herbivorous giants. These in turn were hunted by predators, and after their death, their remains became food for smaller creatures and fertilized the soil. Life in the Jurassic period was characterized not only by a constant struggle for survival, but also by astonishing evolutionary processes. It was during this time that the first primitive mammals appeared on the planet. They were tiny, hid in deep burrows, and were primarily nocturnal to avoid becoming easy prey for the enormous dinosaurs. But it was these inconspicuous, timid creatures that were destined in the distant future to become our ancestors. The Jurassic period was a time when nature itself seemed to have decided to demonstrate the full extent of its imagination. In the forests, where pristine silence reigned and the damp scent of pine needles hung in the air, everything around breathed life. Every tree, every river, every lake became a stage where small dramas played out and great evolutionary discoveries were made. Gigantic herds of sauropods slowly trudged across the endless plains. Their size was unimaginable. Their long tails served as formidable weapons against predators, and their necks, like crane arms, stretched to the very tops of the trees. But there was something peaceful and calm about these majestic creatures. They moved leisurely, as if the earth itself supported them. A special harmony reigned within the herd. Adults protected their young, and the young in turn instinctively remained in the very center of the group, securely protected. Allosaurus and other large predators wouldn't have dared to attack such a herd without a fight. Hunting an adult sauropod was a deadly risk, so their prey most often fell to young, sick, or weakened animals. This was reminiscent of the cruel but just law of nature. Only the strongest survives. It resembled an elongated sack with ring-shaped folds and could likely crawl slowly along the bottom, contracting its primitive muscles. This was a faint but distinct hint of the future, an era when animals would become agile, fast, and capable of actively hunting and escaping danger, But for now, movement was a rarity. The vast majority of Ediacaran creatures preferred to lead a sedentary lifestyle, attached to the bottom or simply lying on it. What's striking is their size. Many of these organisms were quite large, reaching tens of centimeters, and some, as we already know, were as much as a meter in length. How did they manage this with such low oxygen levels in the water? How could they sustain life in such a large body without a complex circulatory system? The answer lies in their unique structure. The vast majority of these creatures were incredibly flat. The enormous surface area relative to their small body volume allowed oxygen to penetrate directly from the water to every cell. Essentially, they were living, breathing carpets, so thin that they required neither lungs nor gills. The Ediacaran world was not static. The planet itself continued to change. Tectonic plates performed their invisible dance, pushing apart continents and forming new ocean basins. Underwater volcanoes erupted, releasing heat and clouds of minerals into the water. These minerals served as fertilizer for photosynthetic organisms, which in turn produced more and more oxygen. And it was precisely this harsh balance that sustained life in the Jurassic world. But Jurassic Earth wasn't just a battlefield. It was a planet where the beauty of future ecosystems took shape. Humid forests buzzed with myriad insects. New species continually emerged, some of them becoming true masters of survival. Bright butterflies, dragonflies with enormous iridescent wings, and beetles whose shells glittered in the sun like precious stones filled the air with their ceaseless movement. They, in turn, became food for small dinosaurs, bird-like creatures, and those very first mammals. One of the most astonishing steps in evolution was the emergence of true feathers. They weren't yet designed for flight, but they already served important functions, keeping warm on cold nights or serving as vibrant decorations in mating rituals. Bright plumage could distinguish males from females, becoming a key element in the struggle for procreation. Gradually, step by step, nature laid the foundation for the distant future when the sky would be filled with the twittering of true birds. The air of the Jurassic period was thick with sound. The shrill cries of pterosaurs mingled with the buzzing of insect wings. The dull rumble of a marching herd of diplodocus was interrupted by the blood-curdling roar of an allosaurus. All of this merged into a single symphony of prehistoric life, so easy to imagine if you just close your eyes for a moment. The seas of that era were in no way inferior to the land in their diversity. Imagine a quiet lagoon, the water so clear that the dark silhouettes of darting ichthyosaurs could be seen through its depths. They constantly surfaced for air, scattering millions of splashes around them, and then immediately dived back into the depths in pursuit of prey. Plesiosaurs hunted near the shores, their serpentine necks writhing as they stalked schools of fish. These creatures seemed to be the living embodiment of ancient sea serpent myths, and in the very heart of the oceans, pliosaurs reigned supreme, the true sea devils of the Jurassic period. Their gigantic jaws were capable of breaking the spine of anyone who dared challenge them with a single blow. An encounter with such a monster meant certain death, and yet even these apex predators were just one part of the great food chain. They did not destroy the world around them, but maintained a fragile balance in it. The key to this incredible flourishing of life was the Jurassic climate. Warmth and high humidity created truly paradisiacal conditions. Winters were mild, and summers were long and hot. Ice caps at the poles did not exist at the time, allowing plants to grow vigorously year-round. Endless forests stretched from the equator to the polar latitudes. Where today lie lifeless deserts or ice-bound lands, life once teemed. But don't think this world was perfect and serene. Jurassic Earth frequently reminded us of its devastating power. Enormous volcanoes erupted, spewing columns of ash and streams of molten lava into the sky. Earthquakes shook the continents, which were still slowly drifting. The supercontinent Pangaea gradually broke apart, and new oceans formed in its place. This monumental process inexorably changed the face of the planet, creating new coastlines, islands, and seas. For the inhabitants of that time, this wasn't a catastrophe, but a natural part of their existence. Dinosaurs adapted, migrated, and colonized new territories. Where volcanoes had burned forests, fresh greenery would emerge years later, attracting herds of animals. The eternal cycle of destruction and rebirth was nature's constant companion. This era holds an important lesson. The grandeur and beauty of the Jurassic period were not the result of rest, but were the fruit of constant, sometimes brutal, change. It was precisely through this constant movement that life evolved, became more complex, and gave birth to ever new forms. The Jurassic period gave our world unforgettable landscapes. Imagine a valley surrounded by craggy mountains, where a herd of Brachiosaurus slowly moves against the crimson sunset. Their dark silhouettes are reflected in the calm waters of a river, while pterosaurs soar silently high above, and somewhere in the distance, the roar of an Allosaurus echoes, a constant reminder that there is no such thing as absolute safety in this world. It was a planet of contrasts, at once peaceful and deadly, beautiful and merciless. The Jurassic period reached its peak, and life on the planet expanded to a scale previously unseen. Gigantic forests sprawled across the continents, where pines, ferns, and ancient cycads rose tens of meters into the sky, intertwining their dense crowns and creating a unique world of semi-darkness beneath their canopy. In these forests, every sound, every rustle, was part of a grand symphony of nature. There, among the intertwined roots and dense thickets, living mountains, Diplodocids, Apatosaurus, and Brachiosaurus sauntered. Their colossal bodies swayed rhythmically with each step, and their long necks, like giant construction cranes, reached to the very tops of the trees, plucking succulent tufts of needles and leaves. Watching them, it became clear why these creatures became symbols of the Jurassic era. They were so enormous that their very presence transformed the landscape around them. Where a herd of brachiosaurs blazed a path through the forest, mighty trees snapped like matchsticks under their weight. The ground turned into a trampled road, and clouds of dust rose into the air. But these giants also played a vital ecological role. They carried plant seeds over vast distances and maintained the delicate balance of this ancient ecosystem. Without them, the forests of the Jura would look completely different. The open plains and swampy lowlands were no less teeming with life. Instead, a brutal war of attrition ensues. The predators pounce again and again, sinking their teeth into the massive legs and sides, leaving deep, ragged wounds. Hour after hour, they torment the colossus until, drained of blood and exhausted beyond repair, it collapses under its own weight. And at that very moment, as the Titan's life ebbs, a bloody feast begins, and the ancient forest echoes with the triumphant, eerie cries of the victors. But not everything in the Jurassic world was steeped in violence and strife. At the same time, in the shadow of the giants, one of the greatest events in the history of the planet was unfolding. For the first time, creatures destined to outlive all dinosaurs took to the skies. The first birds, Archaeopteryx, a creature with feathers almost indistinguishable from modern ones, but with a mouth full of sharp teeth and claws on its wings, became a living bridge between two worlds, a symbol of the evolutionary transition from reptiles to birds. It fluttered through the treetops, gliding from branch to branch in pursuit of small lizards and large insects. Its appearance was proof that evolution never stops. Dinosaurs began to conquer the air, opening a completely new page in the book of life. The Jurassic skies were a truly vibrant and deadly place. Giant pterosaurs soared through the skies like living gliders, masterfully exploiting warm air currents to stay aloft for hours without flapping a wing. The wingspan of some of these creatures rivaled that of a modern bus. Their elongated jaws, studded with needle-like teeth, were the perfect tool for snatching fish straight from the sea waves. Their powerful leathery wings made them absolute masters of the skies. But the sky wasn't theirs alone. Whole flocks of smaller pterosaurs darted through the air, hunting insects and creating living, constantly shifting clouds. The ocean depths of the Jurassic period teemed with their own, no less dramatic life. The seas were home to plesiosaurs, with their incredibly long serpentine necks, and ichthyosaurs, strikingly similar to modern dolphins. These marine reptiles were absolute masters of the underwater kingdom, and every hunt was a true spectacle. Just imagine, a school of ichthyosaurs, like torpedoes, darts through a school of fish, while somewhere in the depths a plesiosaur lurks, ready at the right moment to make a lightning-fast lunge with its long neck and snatch its unsuspecting prey. The aquatic environment was no less teeming with life than the land. The climate during that era remained consistently warm and humid. There were no ice caps on the planet, and even in the polar latitudes, mild, comfortable weather prevailed. These were truly paradisiacal conditions for the thriving of both plant and animal life. Endless forests covered virtually the entire land surface, and the vast plains and swampy lowlands teemed with life. It lasted nearly 80 million years, longer than the entirety of our post-dinosaur era. It was during this time that Earth began to take on the shape we know so well today. Continents continued to drift apart. The climate underwent dramatic changes, and life on the planet reached an unprecedented flourishing and diversity. It was a world filled with colossal lizards, revolutionary new plant species, and the first tiny mammals, still hiding in the shadows of the giants, but already poised to one day take their place in the sun. At the beginning of the Cretaceous, the world map was a gigantic mosaic of slowly drifting continents. Ancient Pangaea had finally broken apart into two supercontinents, Laurasia in the north and Gondwana in the south. Between them, like a slowly healing wound on the planet's body, the Atlantic Ocean was widening, still narrow and shallow, but already clearly delineating the future boundary between the Old and New Worlds. Sea levels rose and water flooded vast tracts of land, creating vast inland seas. This made the planet's climate even milder and wetter. The weather during the Cretaceous period was exceptionally warm. Even at the poles, there was no hint of ice. Where kilometer-thick glaciers lie today, dense forests grew back then, inhabited by dinosaurs adapted to the long polar nights. The average annual temperature on the planet was much higher than it is today. Endless coniferous and fern forests stretched virtually everywhere. But it was then that an event occurred that forever changed the face of the earth. The first flowering plants appeared. Until then, the landscapes had been rather monotonous. Conifers, giant horsetails, cycads, and ferns. The appearance of flowers was a true revolution. They grew much faster. Their leaves and seeds were more nutritious, and their brightly colored corollas began to attract insects, which also experienced an explosion of evolutionary diversity during this period. The emergence of bees, ants, and many other familiar insects is directly linked to the flourishing of this new plant kingdom. The Cretaceous fauna was staggering in its scale. Dinosaurs, at the pinnacle of their evolutionary development, reigned supreme on land. On the northern and southern continents, isolated from each other, completely different species thrived, perfectly adapted to their local conditions. Packs of swift theropods roamed Asia, such as velociraptors, small but incredibly intelligent and deadly predators that hunted in coordinated packs. The first horned dinosaurs appeared in North America and Europe, such as Protoceratops, the ancestor of the famous Triceratops. And in South America and Africa, true titans walked the earth. Giant sauropods like Argentinosaurus, which reached over 30 meters in length and weighed up to 70 tons, the equivalent of a dozen adult elephants. These were the last giants of their kind, living mountains of flesh and bone. The predators were no less terrifying. The chemical composition of the ocean slowly but steadily changed, becoming increasingly favorable for life. Oxygen concentrations increased, while levels of toxic compounds like hydrogen sulfide decreased. And what about the land? On land, there was absolute emptiness. The continents of that time were lifeless landscapes of bare rock, sandy deserts, and endless plains. There wasn't a single plant, not a single bush. Soil as we know it didn't exist either, only bare, crushed rock, devoid of organic matter. Rainstorms lashed these dead landscapes, and raging torrents washed tons of sediment into rivers, which carried it out to the ocean. Perhaps only on damp coastal rocks could one find thin films of bacteria or algae, but nothing more complex. The climate during the Ediacaran period was surprisingly mild. After the end of the Great Ice Age, the planet entered a phase of global warming. Polar ice caps likely did not exist, and even at high latitudes, moderate temperatures prevailed. The oceans were warm, especially at the equator, where water temperatures could reach 30 to 35 degrees Celsius. Powerful currents distributed this warmth across the planet, creating a stable and predictable climate. There were no abrupt seasonal changes, no icy winters, no sweltering summer heat. It was a calm, gentle world, as if the planet were resting after the ice storms of the past. And in this quiet world, nature conducted its first great experiments. Giganotosaurus hunted in South America and Spinosaurus aegyptiacus, a huge predator with a crest on its back and a long crocodile-like snout, perfectly adapted to life in the water, prowled Africa. But at the top of the food chain in North America reigned Tyrannosaurus rex, perhaps the most famous dinosaur in history. This monster, reaching 12 meters in length, possessed jaws of monstrous strength, capable of crushing even the thickest bones with ease. It became a living symbol of the entire Cretaceous period and the embodiment of the primeval might of the age of dinosaurs. But the world wasn't limited to dry land. The seas and oceans literally teemed with life. Their warm waters swam giant predatory reptiles, mosasaurs, long-necked plesiosaurs, and their swift relatives. These creatures ruled the ocean, hunting fish and ammonites and not hesitating to even attack each other. Ammonites, mollusks with beautiful spiraling shells, were found in countless numbers and served as a vital link in the marine food chain. Pterosaurs soared in the skies. During the Cretaceous, they reached record sizes among all flying creatures that have ever lived on Earth. Quetzalcoatlus, which lived at the very end of the era, had a wingspan of up to 12 meters, larger than many modern light aircraft. Parallel to the dominance of these giants, another quiet but no less important story unfolded in the shadows. Tiny mammals, primarily nocturnal and feeding on insects, became increasingly diverse. Among them were already primitive marsupials and placental forms, the direct ancestors of those who shortly after the extinction of the dinosaurs would conquer the entire planet and occupy all the vacant ecological niches. In the Cretaceous, they were still hiding in burrows, but it was then that the foundations of the future mammal kingdom were being laid. However, this wondrous and rich world did not last forever. At the end of the Cretaceous period, one of the most horrific catastrophes in the history of our planet occurred. Approximately 66 million years ago, a gigantic asteroid, approximately 10 kilometers in diameter, crashed into Earth. It smashed into what is now the Yucatan Peninsula in Mexico, leaving behind a gigantic scar, the Chicxulub crater. The force of the impact was unimaginable. The energy of the explosion was millions of times greater than the power of humanity's entire nuclear arsenal. In an instant, firestorms, gigantic tsunamis, hundreds of meters high, and deadly acid rain swept across the planet. Billions of tons of dust and soot were released into the atmosphere, blanketing the entire planet in a thick shroud and blocking sunlight for months, possibly years. The climate changed catastrophically. Temperatures plummeted and plants deprived of light began to die. Herbivores followed suit, and then predators died out of starvation. Dinosaurs, which had ruled the Earth for over 160 million years, disappeared almost entirely. Only a few of their descendants, the ancestors of modern birds, managed to survive. Marine reptiles, pterosaurs, and ammonites all vanished into oblivion. But mammals, birds, insects, and flowering plants managed to survive this catastrophe and ushered in a new era, the Cenozoic, an era in which mammals, not dinosaurs, would become the new masters of the Earth. The Cretaceous period marked the grand finale of the dinosaurs' reign. It gave the world unprecedented life forms, forever changed ecosystems with the emergence of flowers, and paved the way for the planet's future development. It was an age of giants, an age of incredible beauty and primordial terror, an age that culminated in a cosmic tragedy that made way for new rulers. Thus ended the Mesozoic era, and a new history began, one that would ultimately lead to the emergence of humans. Let us fast forward hundreds of millions of years into the past to a world our planet will never see again. This is an era where time flows differently, and evolution takes its first grandiose steps. But these strange creatures, resembling living carpets and feathers, were far from alone in the primeval oceans. The entire water column was permeated with myriads of microscopic algae, which wove together into dense clouds, giving the seas a mysterious greenish hue. The sea floor was covered with a continuous sticky blanket of bacterial mats. Some of these mysterious creatures could move leisurely across this sticky surface as if on a living carpet. These bacterial layers were so strong and dense that they literally cemented the bottom sediments, protecting them from being washed away by underwater currents. It is precisely because of this unique circumstance that the imprints of Ediacaran life are forever frozen on the sea floor of ancient seas. These are the very fossil evidence that paleontologists today extract from the rock strata, allowing us to peer into this long-gone universe. The very process of fossilization in the Ediacaran period was a true miracle. After all, soft-bodied creatures are usually doomed to disappear without a trace. After death, their tissues rapidly decompose, leaving nothing behind. But bacterial mats created truly unique conditions for preservation. Imagine, a creature reaches the end of its life and descends onto a sticky bacterial carpet. And then the magic begins. Like invisible sculptors, bacteria immediately envelop its body, creating a delicate mineralized cast. Silt and sand slowly cover it, and over millions of years, this imprint turns to stone. Thanks to this incredible process, we can now examine the structure of Ediacaran creatures with astonishing clarity. Every fold, every segment, every textured detail of their enigmatic bodies. One of the greatest mysteries of paleontology surrounding the Ediacaran biota is the question of their place on the tree of life. Were they our distant ancestors, or did they represent a completely separate, dead-end evolutionary lineage that eventually became completely extinct? The scientific community still hasn't reached a consensus. Some researchers believe that individual Ediacaran organisms, such as Cambrian, may have been the ancestors of mollusks. This oval-shaped creature had a wide soul, which it apparently used to slowly crawl along the seabed, and on its back it carried something resembling a primitive shell. If this is indeed the case, then we are looking at a crucial link in the evolutionary chain, one of the first steps toward the emergence of animals with hard body parts. However, other scientists are far more skeptical. They point out that most Ediacaran creatures possessed a structure unmatched by any modern animal group. Their strange radial or even triradiate symmetry, the complete absence of any digestive system, and their unusual body segmentation all hint that they may have been nature's grand experiment, an attempt to create multicellular life according to entirely different blueprints, which ultimately lost the evolutionary race. Perhaps the entire Ediacaran fauna was, if you will, Plan A, discarded in favor of the far more successful Plan B, animals with hard skeletons, active, agile, and capable of complex behavior. But whether they were our distant ancestors or merely a dead-end branch of evolution, Their contribution to the history of life on Earth cannot be overstated. They proved that multicellularity is not just a fantasy, but a working mechanism. They revealed to the world the incredible diversity of forms that life is capable of. They created the first ecosystems in the history of the planet, where different organisms interacted with each other, albeit in a primitive manner. And most importantly, they set the stage for the most grandiose and dramatic event in the history of life on our planet, the Cambrian Explosion. By the end of the Ediacaran era, approximately 541 million years ago, the world stood on the threshold of colossal changes. Oxygen levels in the oceans continued to rise steadily, approaching modern levels. This was like pouring high-octane fuel into the engine of evolution, creating conditions for the emergence of far more active and energetic creatures. At the same time, the chemical composition of seawater was also changing. The concentration of calcium and other minerals increased, providing living organisms with the building blocks for constructing strong shells and skeletons. These changes occurred gradually over millions of years, but their cumulative effect was truly revolutionary. The first signs of the coming storm appeared in the form of tiny hard structures, microscopic tubes, plates, and needle-like structures that some organisms had learned to create. But their legacy lives on in every multicellular organism on our planet, in each of us. We carry within us the genetic memory of this ancient era, encoded in the structure of our cells, in the very possibility of our existence. The Ediacaran period was more than just a chapter in Earth's history. It was the very beginning of a great saga of complex life, a story that is still being written today. And then, 541 million years ago, something incredible happened. In just 25 million years, a blink of the geological clock, our planet's oceans literally exploded with an unprecedented diversity of life. This event was so swift and dramatic that scientists aptly named it the Cambrian Explosion. If the Ediacaran era was a quiet, slow prelude, then the Cambrian became a thunderous overture to the grand opera of life that has been unfolding on our planet for over 500 million years. What happened? Why did evolution suddenly decide to experiment with such frantic abandon? The answers to these questions lie in a complex nexus of environmental, geological, and genetic factors. Oxygen levels in the oceans reached critical levels, enabling animals to develop a rapid, energy-intensive metabolism. The concentration of minerals, primarily calcium, increased to such a degree that organisms were able to build durable shells and armor. But perhaps the main spark that ignited this evolutionary fire was the emergence of a new, terrifying phenomenon: predation. For the first time in Earth's history, some animals began to deliberately hunt others, and this launched an unprecedented arms race between predators and their prey. Let's dive into the waters of the Cambrian Sea. The water here is warm and crystal clear, saturated with oxygen. Sunbeams penetrate to the very bottom, creating a whimsical play of light and shadow in the shallows. But this is no longer the realm of silence and peace of the Ediacaran era. Here, everything is seething and moving. Strange arthropods, resembling a hybrid of a shrimp and an armadillo, scurry along the bottom like miniature armored cars. Jellyfish pulsate in the water column, rhythmically contracting their translucent bodies. Motionless creatures in shells which force water through themselves, filtering food, lie frozen on the rocks, and somewhere there, in thickets of ancient algae, he lurks, the most dangerous hunter of his time. A creature with gigantic bulging eyes and deadly grasping appendages. Its name is Anomalocaris, and it is a true terror of the Cambrian seas. Reaching almost a meter in length, it was a true giant compared to its contemporaries. Its segmented body was protected by a flexible yet durable shell. Paddle-like appendages extended along its sides, propelling it with wave-like movements as it glided through the water. But its most formidable weapon was its front appendages, long, segmented, and studded with sharp spines. Anomalocaris used them like hands to grasp its prey and bring it to its mouth. And its mouth was truly terrifying. A round opening framed by a ring of sharp plates that met like a camera aperture, easily crushing the shells of its unfortunate victims. For a long time, paleontologists couldn't piece this puzzle together. Parts of Anomalocaris were found separately and mistaken for entirely different creatures. Its front appendages were thought to be the body of some ancient shrimp. Its mouth parts were mistaken for a fossilized jellyfish, and the body impression itself was mistaken for a sea cucumber. Only when a complete, well-preserved skeleton was discovered did scientists realize that all these fragments belonged to the same incredible apex predator. Anomalocaris was the pinnacle of evolution in its era, a creature that reigned supreme at the top of the food chain in the Cambrian oceans. But Anomalocaris was the king, not the only hunter. In this new, brutal world, the Cambrian seas literally teemed with predators of all shapes and sizes. There were also small worms with sharp jaws that hid in the bottom sediments to suddenly snatch unwary prey. There were also arthropods with powerful pincers. Even among animals we today consider harmless filter feeders, predatory species were present in the Cambrian period. The emergence of predation forever changed the rules of the evolutionary game. Simply existing and absorbing nutrients was no longer enough. The Ediacaran biota, as scientists call the collection of these strange organisms, was history's first attempt to create complex multicellular life forms. But, as often happens with early attempts, it proved a dead end. The vast majority of these amazing creatures left no direct descendants. They simply died out at the end of the period when conditions on the planet changed dramatically again. But they fulfilled their primary mission. They paved the way for those who came after them. They proved that life can be vast, complex, and diverse. What destroyed this strange and wonderful world? Why did the Ediacaran biota disappear from the face of the earth? The answer lies in the events that unfolded at the boundary between the Ediacaran and the following Cambrian periods. Approximately 541 million years ago, the oceans began to change again. Oxygen levels continued to rise, reaching previously unseen heights. This opened up entirely new evolutionary opportunities, but also presented new challenges. In these now oxygen-rich waters, entirely new types of organisms began to emerge. Creatures clad in hard shells, armed with sharp teeth, and driven by predatory instincts. A new era was dawning, an era of brutal struggle and merciless competition, an era in which there was simply no room left for the soft-bodied and defenseless creatures of the Ediacara. But before we enter this new, furious world, let us linger for a moment in the tranquil waters of the Ediacara Sea. Defense was now essential, and the answer to this threat was not long in coming. In a remarkably short time, a huge number of organisms acquired hard protective structures. Trilobites, among the most successful and numerous animals of the Cambrian, covered their bodies with a segmented shell of calcium carbonate. But this wasn't just crude armor, it was a true work of engineering art. A complex system of joints allowed the trilobite to curl up into an impenetrable ball when threatened, just like a modern armadillo. Imagine a world where vision had only just emerged. It was during this era that trilobites, the true rulers of the ancient seas, developed the first complex eyes in the history of the planet. These were not simple light-sensitive spots. Their visual organs were a complex mosaic of numerous tiny lenses, each creating its own fragment of the overall picture. This design gave these arthropods an incredibly wide, almost panoramic field of view, allowing them to instantly detect any shadow or movement that might signal the approach of a deadly threat. Brachiopods lived alongside them on the seafloor. Outwardly, they can easily be confused with modern bivalves, such as mussels or oysters. But this resemblance is merely deceptive. In fact, they belong to an entirely separate, distinct branch of the tree of life. Their bodies were encased in a strong, double-valved shell, which served as a secure shelter. And from this fortress protruded a special muscular foot, which the animal used to firmly attach itself to underwater rocks. Brachiopods were tireless filter feeders. They continuously swirled seawater through themselves, catching microscopic food particles with specialized ciliated tentacles. In the Cambrian seas, they reproduced in such incredible numbers that they formed entire underwater cities, covering the sea floor with a continuous carpet of their shells. And of course, the Cambrian period became the cradle of mollusks, a group destined to become one of the most prosperous on Earth. Their first representatives were incredibly simple, tiny creatures with a single cone-shaped shell slowly crawling along the seafloor, scraping off a film of algae or consuming organic remains, so-called detritus. But even these simple creatures displayed an incredible adaptive potential that, in future eras, would allow their descendants to conquer every conceivable corner of the world's oceans, from bottomless, inky trenches to tidal shores, and even achieve the unthinkable, make it onto dry land. Perhaps the most astonishing and mysterious inhabitants of the Cambrian waters, however, were those whose evolutionary lines ended without leaving direct descendants. Before us is a creature known to science as hallucigenia. Its remains completely baffled scientists for years. It resembled a living oval pincushion, covered in long protective spines and tiny scales like chain mail. It slowly crawled along the bottom, methodically scraping bacterial mats and algae from the rocks. And here's the morella, a small arthropod with graceful feathery appendages and 2 pairs of long antennae. Judging by the number of finds, it was one of the most common creatures of the Cambrian period. But among all this diversity, there's one creature, seemingly inconspicuous at first glance, that holds special significance for us: Pikaia. This small, eel-like creature possessed a notochord, an elastic rod that was a primitive precursor to the spine. This fact makes Pikaia one of our most ancient known relatives, an early representative of the chordates. that same great group of animals to which 500 million years later we will belong. The Cambrian period was a time of great experimentation. Nature, like a brilliant but mad sculptor, explored a wide variety of design plans for living organisms. It was then, in this short period of time by geological standards, that virtually all modern animal phyla appeared on the stage of life. Arthropods, mollusks, various worms, echinoderms, and chordates. But alongside them, there were also forms that defy any modern classification. These strange wonders of the Cambrian clearly demonstrate that evolution did not follow a straight path. It branched off in hundreds of different directions, testing all manner of possibilities, and most of these early experiments ultimately proved to be dead ends. But why did this explosion of diversity occur precisely then, in the Cambrian? One leading theory holds that the emergence of eyes was the trigger. The ability to see was a game changer. Predators could now track their prey from a distance, and prey gained the chance to spot danger and flee. This triggered a merciless evolutionary arms race. Predators honed their vision, developed lightning-fast reflexes, and deadly prey-capturing weapons. Their prey, in turn, responded by developing protective armor, sharp spines, and the ability to burrow or swim away instantly. Each new invention by predators immediately necessitated a countermeasure by their prey, and this cycle repeated itself endlessly. Another hypothesis points to changes at the genetic level. Around this time, entire sets of genes in the DNA of ancient organisms were duplicated. This provided evolution with much more raw genetic material for experimentation. Genes responsible for body development became more complex and flexible. So-called homeobox genes emerged, a kind of master switch that controls the formation of various body parts along the main axis, from head to tail. This new genetic toolkit allowed evolution to create new life forms at incredible speeds simply by changing the combinations and sequence of activation of these genes. The climate of the Cambrian era was paradisiacal. The planet had no polar ice caps, and sea levels were very high. This created endless shallow seas that flooded the edges of the continents, an ideal environment for a thriving marine life. The continents themselves continued their slow drift, with most of the land mass at that time clustered in the southern hemisphere. Between them, the oceans expanded, creating a vast diversity of marine habitats, from warm tropical waters to cooler temperate zones. The atmosphere continued to become saturated with oxygen. Its level was still lower than today, perhaps ranging from 15 to 18%, but this was already sufficient to support active, mobile life in the oceans. At the same time, the concentration of carbon dioxide in the air was high, creating a powerful greenhouse effect and maintaining a warm climate across the planet. The sky overhead may not have had the same deep blue hue as today due to the different gas composition, but the sun shone just as brightly, providing energy to billions of photosynthetic organisms in the ocean waters. And on land, a deathly silence still reigned. The continents were lifeless deserts of bare rock and sand, but at the very boundary of land and sea, in the intertidal zone, the first modest colonists, mats of algae and cyanobacteria, were already beginning to establish themselves. These primitive communities slowly but surely prepared the ground for future land conquest. They initiated the very first process of soil formation in history, breaking down rock and accumulating organic matter. However, the emergence of true terrestrial ecosystems would still be a very, very long time away, more than 100 million years. Meanwhile, in the Cambrian oceans, food chains became increasingly complex and multi-tiered. At the very base were the producers, algae and cyanobacteria, which converted sunlight energy into food. At the next level were their eaters, filter feeders and scrapers like trilobites, mollusks, and brachiopods. These, in turn, were hunted by smaller predators, predatory worms, and small arthropods. And at the very top of this pyramid sat the true giants of the era, such as Anomalocaris. This complex hierarchy created an intricate web of interactions in which the life of each organism was inextricably linked with dozens of others. Reef structures in the Cambrian weren't built by corals as they are today. This role was performed by archaeocyathids, mysterious creatures resembling porous, double-walled cups. Archaeocyathids were filter feeders and grew in such dense colonies that they formed true reefs in warm, shallow seas. These ancient reefs became home and refuge for a multitude of other organisms, trilobites, worms, and small arthropods. But the archaeocyathids' life was short-lived. By the end of the Cambrian, they had completely died out, and for millions of years, the planet was left without true reef builders until corals took over this ecological niche. Trilobites were the undisputed stars of the Cambrian seas. They diversified into a vast number of species, adapted to a wide range of conditions. There were tiny trilobites, no larger than a pinhead, scurrying about in the bottom mud. There were also true giants, over 1/2 meter long, slowly crawling along the seafloor. There were planktonic species, floating freely in the water column. There were also blind trilobites, living in deep, murky waters where vision was completely useless. And some species evolved enormous spines to protect themselves from predators. This incredible diversity demonstrates how successful the basic trilobite body design was. A segmented torso, covered in a tough shell and a multitude of specialized limbs. Interestingly, trilobites, like all modern arthropods, molted. As they grew, they shed their old cramped shell and grew a new, larger one. This is why fossils of shed shells are found in rocks far more often than the remains of whole animals. This suggests that each trilobite molted multiple times during its life. Some species possessed a remarkable ability. When threatened, they would curl up into a tight ball, concealing their vulnerable ventral side beneath a robust armor. Fossils of such curled-up trilobites are moments frozen in stone of mortal danger, when the defense mechanism was triggered seconds before the animal was buried beneath sediment. By the middle of the Cambrian period, Earth's oceans had become a veritable cauldron of life. The diversity of forms, colors, and lifestyles was astounding. Animals swam, crawled, burrowed, sat still, hunted, and fled. They employed every conceivable survival strategy, from heavy armor and venomous spines to fast swimming and camouflage. Ecosystems became incredibly complex and interdependent, where the extinction of a single species could trigger a chain reaction and affect the fate of many others. But don't think that the Cambrian period was just a time of unclouded prosperity. It was also an era of great extinctions. Several times during this period, catastrophic events occurred, resulting in the disappearance of a significant portion of life on the planet. The causes of these events are not fully understood, but they were most likely related to abrupt changes in sea level, fluctuations in oxygen levels, and possibly even powerful volcanic activity. Each such extinction, however, cleared the way for survivors. They gained new capabilities and quickly evolved to occupy the vacated ecological niches. By the end of the Cambrian period, about 445 million years ago, the ocean world already looked completely different than at its beginning. Life's great experiment continued. Fast forward to that turning point, when the turbulent Cambrian era was drawing to a close. The world was changing. Many of the bizarre experimental life forms that first populated the ancient oceans began to disappear from the scene. The great reef builders, the archaeosaurs, disappeared forever, and the formidable Anomalocaris and its mighty relatives, once the undisputed masters of the seas, became rare, fading giants. But nature abhors a vacuum. One was replaced by another. Trilobites, those armored knights of the prehistoric seafloor, were enjoying their finest hour. Brachiopods and mollusks flourished alongside them, filling the vacant ecological niches. And then, amid this riot of invertebrate life, the first, barely noticeable harbingers of the future appeared. These were tiny, jawless creatures, more worm-like than fish-like, possessing a primitive notochord, the ancestor of our spine. They were humble and unremarkable inhabitants of the seafloor, but it was these inconspicuous creatures that were destined to completely revolutionize the course of evolution in the coming era. The Cambrian Explosion was a true crucible of creation, a turning point in the annals of our planet. In a geologically insignificant period of time, such a staggering diversity of living organisms emerged that it laid the foundation for the entire subsequent history of the animal kingdom. Imagine this lost paradise, endless shallows pierced by sunlight and strange, dreamlike life forms lining the bottom. There are no sounds, no bustle, only the measured, almost imperceptible movement of the water and the gentle sway of mysterious creatures. This is a world of absolute silence and peace, a world where time flowed unbearably slowly and change took millions of years. Let us move on to a world where moisture-loving club mosses and horsetails were replaced by new masters of the forests. These were chordates, the distant ancestors of modern conifers, far better adapted to arid conditions. They preferred to settle at higher elevations, far from the vast swamps, and their appearance heralded a coming era when conifers would rule the land. These ancient forests were incredibly productive. Vegetation grew at a breakneck pace, voraciously absorbing carbon dioxide from the atmosphere and basking in the rays of the ancient sun. As giant trees reached the end of their life cycle, they collapsed into dark, swampy waters. Here, at the bottom, conditions reigned, virtually devoid of oxygen. In a normal world, dead wood would become food for fungi and bacteria, which, by decomposing it, would return carbon to the atmosphere. But in the airless mire of the swamps, this process was almost completely halted. Fallen trunks piled up on top of each other, forming thick layers. Virtually all modern animal phyla we know today trace their lineage back to those very same depths, the Cambrian seas. This means that the fundamental blueprints of body structure What distinguishes an arthropod from a mollusk and a creature with a backbone from a starfish were developed and solidified back then, more than 500 million years ago. To glimpse this lost world, we must travel to the Burgess Shale in the Canadian Rockies. These aren't just rocks, they're a veritable window into time, a frozen scene from a prehistoric drama. Here, in sediment some 505 million years old, thousands of fossils have been preserved in astonishing clarity. And the most incredible thing is that not only hard shells but also soft tissues have been preserved. Imagine, we can see the imprints of the muscles that moved these creatures, their intestines, gills, and even their eyes. This allows paleontologists to reconstruct the appearance of ancient animals in stunning detail, understanding how they lived, what they hunted, and how they navigated their aquatic environment. The Cambrian period clearly demonstrated that evolution can move at incredible speed when the right conditions are in place. The emergence of the first true predators, the development of vision, the rise of oxygen in the atmosphere and water, and the emergence of new genetic mechanisms that allowed for rapid changes in body structure, all these factors converged, creating a perfect storm for evolutionary innovation. The result was that explosion of diversity, the echo of which we see in every living thing on Earth to this day. But the oceans couldn't remain the realm of invertebrates forever. Already at the end of the Cambrian, the first vertebrates appeared on the scene, those tiny, jawless fish that would one day give rise to all fish, amphibians, reptiles, birds, and mammals, including us. The great drama of life on Earth was ready for its next act. Approximately 485 million years ago, our planet's oceans entered a new monumental era. The Cambrian Explosion had died down, but the evolutionary flywheel continued to spin. On the contrary, life continued its endless experiments, exploring new horizons and creating ever more complex forms. The Ordovician period had begun, a time of true flowering for marine fauna, a time when the ocean depths teemed with an unprecedented diversity of creatures. If the Cambrian was the era of the creation of the basic blueprints for living organisms, then the Ordovician was the era of their refinement, improvement, and specialization. For most of this period, the planet's climate was warm and remarkably stable. There were no ice caps at the poles, and sea levels were among the highest in Earth's history. Vast tracts of the continents were covered by shallow tropical seas, which became a veritable paradise for nascent life. These seas, which scientists call epicontinental, were warm, sunlit, and rich in nutrients. It was here, in these vast shallows, that the main drama of the Ordovician era unfolded. At that time, the world map looked completely different. The continents were huddled together primarily in the southern hemisphere, the gigantic supercontinent Gondwana, which encompassed what would later become Africa, South America, Antarctica, Australia, and India, was slowly drifting toward the South Pole. To the north lay smaller land masses, Laurentia, which would later form North America, and Baltica, the future Scandinavia and Eastern Europe. Between these land masses stretched the boundless Panthalassa Ocean, the ancestor of the Pacific Ocean, as well as the smaller oceans Iapetus and Rhea. The water in the Ordovician seas was crystal clear in some places and turbid with swarming plankton in others. Temperatures in the tropics could reach 45 degrees Celsius, significantly hotter than in modern tropical seas. In temperate latitudes, the water was cooler, around 20-25 degrees Celsius, but still created comfortable conditions for life to thrive year-round. Ocean currents carried heat from the equator to the poles, maintaining a relatively equable climate on the planet. The Ordovician atmosphere contained more carbon dioxide than it does today, but its concentration gradually decreased. Oxygen levels, on the other hand, continued to rise slowly, reaching approximately 18 to 20%. This was sufficient to support active life not only in the water, but also for the first, most tentative attempts of living organisms to emerge onto dry land. The sky overhead may have had a slightly different shade of blue due to the different gas composition, but the sun shone as brightly as it does today, feeding the endless fields of algae in the shallows with its energy. Trilobites, the stars of the Cambrian, showed no sign of giving up their position. In the Ordovician, they underwent a new evolutionary cycle, giving rise to an even greater number of species adapted to a wide variety of conditions. Among them were microscopic forms that lived among the grains of sand on the seafloor, as well as true giants whose bodies reached over 70 centimeters in length. Species emerged whose shells were covered in enormous spines, protruding in all directions, like the armor of a medieval knight. Some trilobites developed incredibly large eyes which allowed them to hunt in the twilight depths. Others, on the contrary, became completely blind, adapting to life in perpetual darkness or murky waters, where vision was utterly useless. But the true masters of the Ordovician seas were now entirely different creatures. Brachiopods now reigned supreme over the shallow reefs. These animals, superficially resembling bivalves, but belonging to a completely different phylum, covered the seafloor in dense colonies. Their shells opened only a crack to allow water to pass through a special organ called a lophophore, a crown of cilia-covered tentacles. These cilia created a constant current of water from which the animal filtered out the smallest food particles. Brachiopods were so successful that in some places they formed veritable underwater meadows, covering every centimeter of the seafloor. They were joined by bryozoans or bryozoans, tiny colonial animals that built elegant, lacy skeletons from limestone. A bryozoan colony could resemble a fan, a branched tree, or an openwork net. Each individual in this colony, a zooid, lived in its own microscopic cell and extended a crown of tentacles to filter water. Thousands of these tiny creatures worked together, creating complex three-dimensional structures that served as home and shelter for numerous other organisms. But the most impressive builders of the Ordovician era were the corals. For the first time in Earth's history, these animals appeared in huge numbers and began to form the first true reef systems. Of course, Ordovician corals were very different from modern ones. They were the so-called tabulata and rugosa corals, groups destined to become completely extinct by the end of the Paleozoic era. These coral reefs were veritable metropolises of the ancient world, teeming with life. Trilobites hid in their crevices, mollusks crawled, and primitive cephalopods, nautiloids, the ancestors of modern octopuses and squid, hovered above the reefs. These Ordovician nautiloids were incredibly diverse. Some had straight conical shells reaching several meters in length. Others had curved shells resembling ram's horns. All were active predators, using their tentacles to capture prey and their propulsion for rapid attacks. One of the largest and most fearsome predators of the Ordovician seas was Cambrian, a gigantic nautiloid with a straight shell that could grow up to 9 meters in length. Imagine a living torpedo the size of a bus. Its enormous shell was divided into chambers that the animal filled with gas, regulating its buoyancy. Anomalocaris slowly floated in the water, scanning for prey with its large eyes. Its dozens of tentacles, adorned with hooks and suckers, were ready to strike at any moment. Spotting an unwary trilobite or ancient fish, this monster would swiftly attack, grabbing its prey and tearing it apart with its powerful sharp beak. It was one of the largest animals of its time, a true tyrant of the seas. But cephalopods weren't the only creatures that terrified the inhabitants of ancient seas. An incredible diversity of eurypterids, or sea scorpions, appeared in the Ordovician. These arthropods, distant relatives of modern scorpions and spiders, were perfectly adapted to aquatic life. Their long, segmented bodies were covered in a tough chitinous shell, and their last pair of limbs evolved into wide paddles, allowing them to move quickly through the water. Their forelimbs were often armed with sharp spines or powerful pincers for capturing prey. Most Ordovician sea scorpions were relatively small, ranging from 10 to 30 centimeters in length, and hunted small invertebrates on the bottom. But even then, larger species also appeared, the harbingers of the giant sea scorpions that would terrorize the seas in the Silurian and Devonian periods. A new era of marine predators was approaching. So let's imagine the bottom of the Ordovician seas. It was not just an underwater world, but a veritable battlefield, where dramas of survival played out daily. Here, among the ancient reefs, lived creatures that combined grace, speed, and deadly weaponry, the perfect killing machines of their time. But let's delve deeper to the very bottom, where its own no less astonishing life teemed. Look, entire underwater meadows stretch out before us, but these aren't plants. These are sea lilies, or crinoids. With their long, flexible stems, they clung to the rocky bottom, and above, they spread out a fan of feathery arms like whimsical flowers to catch floating food particles. These amazing creatures were related to starfish and sea urchins, belonging to the large group of echinoderms. Their skeletons, composed of calcareous plates, settled to the bottom after death, and over millions of years they formed entire limestone layers that paleontologists still find today. During the Ordovician period, these underwater crinoid forests reached an incredible flowering, covering vast expanses of shallow seas. And here come their more agile relatives. Sea stars and their nimble cousins, the brittle stars, also known as brittle stars, slowly crawl along the seabed. The starfish is a slow but relentless predator. We see it slowly covering a bivalve shell with its body, and a deadly confrontation begins. With the power of its tiny legs, it gradually forces the shells apart to reach the tender meat inside. Brittle stars, far more agile creatures, dart nearby. With their long, sinuous arms, they move quickly across the uneven terrain in their eternal search for food. And somewhere around here, we can spot the first sea urchins. Their evolutionary journey was just beginning, but even then, their spherical shells, studded with sharp, mobile spines, became a reliable defense in this dangerous world. Mollusks, too, were not standing still, continuing to master new life strategies. Take bivalves, the ancestors of modern mussels and oysters. Some of them burrow into soft sand, exposing only their breathing siphons, while others firmly adhere to rocks and reefs. And gastropods, snails of all shapes and sizes, crawl along the surface. With their unique organ, the radula, which resembles a grater-like tongue, they scrape algal deposits from rocks, but evolution pushed some of them down a darker path. Look, here's a predatory snail that has developed a terrifying hunting method. It literally drills a hole in the shell of another snail or mollusk to suck out its defenseless prey. But this wasn't the most monumental, truly revolutionary event of the Ordovician period. New players, vertebrates, entered the stage, while in the Cambrian they were represented only by tiny, primitive, jawless creatures, more like juveniles. Everything changed dramatically. In the Ordovician, the first true fish appeared, although they looked completely different from their modern descendants. These pioneers belonged to the group of agnatha, or jawless animals. They lacked the familiar mouth with jaws. Instead, they had a round mouth opening, a true living sucker, often studded with tiny horny teeth. They couldn't bite their prey, but they could latch on and scrape food or simply filter it from the water. Their bodies were clad not in scales, but in heavy, bony armor, especially in the front. This armor protected them from numerous predators, but it also made them slow and clumsy underwater tanks. One of the most famous groups of these armored fish is the ostracoderms, which literally means armored. Imagine a creature with a heavy, bony helmet covering its head and front half, while its tail remained flexible and mobile, covered only with small scales. They swam clumsily near the bottom, pushing off with their tails, and like living vacuum cleaners, sucked up silt and small invertebrates from the bottom. Their eyes, located on the sides or even on top of their heads, constantly scanned the sky, that is, the water above them, for the shadow of approaching danger. The emergence of vertebrates was a true breakthrough. An internal skeleton made of bone or cartilage offered incredible advantages. It provided reliable internal support, allowing the body to grow to unprecedented sizes without becoming too heavy. Powerful muscles were attached to this framework, making movements much more efficient and powerful. And, of course, it protected the most vital organs, the brain and the spinal cord running through the entire spine. As the skeleton grew, so did the nervous system. The brain of vertebrates was larger than that of invertebrates, paving the way for more complex behavior, instincts, and reactions. But let's not get ahead of ourselves. In the Ordovician seas, vertebrates were still modest and unnoticeable inhabitants. They didn't rule the oceans, and they weren't the largest or the fastest. Under the colossal weight of new sediments and the effect of the Earth's heat, this compressed plant matter slowly over millions of years underwent a geological alchemy. First it turned into peat, and then under even greater pressure into brown coal, and finally into coal. This monumental process, spanning an entire eon, led to the formation of the gigantic coal deposits that humanity uses today. The vast majority of the world's coal reserves were formed during this period, which is not without reason called the Carboniferous period. Such large-scale carbon storage inevitably affected the planet's climate. the carbon dioxide extracted from the air by plants and locked in coal seams, no longer created a greenhouse effect. As a result, its concentration in the atmosphere began to steadily decline, from 2,500 to 2,000 parts per million at the beginning of the era to only 300 to 400 parts per million by its end. This caused global cooling, which was particularly pronounced in the polar latitudes. But the Carboniferous atmosphere was unique for more than just this. It was supersaturated with oxygen, a true boon for insects. In this environment, they could grow to sizes that seem unimaginable to us today. Imagine Meganura, the giant dragonfly of that era. Its wingspan reached 75 centimeters, like a modern hawk. To this day, it remains the largest insect ever to soar in Earth's skies. This was the time of giant cephalopods, enormous eurypterids, and countless arthropods. Vertebrates remained somewhere on the evolutionary fringes, slowly, generation after generation, accumulating the very traits that would one day allow their descendants to conquer not only the oceans, but also land. Meanwhile, changes were also beginning on land. True forests were still a long way off, but the first living organisms were already taking tentative steps toward colonizing coastal areas. Green carpets of algae and cyanobacteria slowly spread further from the water's edge, covering the damp rocks and soil. The first lichens also appeared, amazing symbiotic organisms, a union of fungus and algae. They were incredibly resilient and could survive on bare rocks in the harshest conditions. It was lichens that initiated the great process of soil formation. With their acids, they slowly broke down the rock, creating the first, most primitive layer of soil. Fungi followed them onto land. These unnoticeable workers played a vital role, decomposing dead organic matter and returning nutrients to the natural cycle. The first terrestrial fungi were likely microscopic, but they laid the foundation for future complex ecosystems. Perhaps it was then that the great partnership of mycorrhiza, a union of fungi and plants, was born, where the mycelium helps the plant extract minerals from the soil, receiving nutritious sugars in return. And then, toward the end of the Ordovician period, another miracle occurred. The first true land plants appeared. They were tiny, just a few centimeters tall. They had no roots, no leaves, no complex vascular system for transporting water. These were creatures like Cooksonia, simple green stems covered in a waxy film to prevent them from drying out in the air. They grew near the water on damp banks, clinging to the soil with thin rhizoid outgrowths. They reproduced by spores carried by the wind. Yes, these pioneers were unimpressive. They didn't even create dense thickets, but they were the first to truly live on land. Their appearance marked the starting point for the colonization of the continents, a process that would take hundreds of millions of years and forever change the face of our planet. The climate during the Ordovician was warm and stable for a long time, but towards its end, truly dramatic events began. The enormous supercontinent Gondwana slowly but inexorably drifted toward the South Pole. As soon as its southern edges reached polar latitudes, the Great Ice Age began. Gigantic ice caps began to grow on land. As the glaciers grew, they drew water from the world's oceans, causing sea levels to drop catastrophically. The consequences were dire. The vast, shallow seas that covered the continental shelves and were the cradle of much life began to retreat, exposing the seafloor. This was a death sentence for their inhabitants. Thriving coral reefs were exposed to the elements, dried up, and turned into graveyards. Countless colonies of brachiopods and bryozoans, perfectly adapted to life in shallow waters, lost their home. The trilobites that swarmed the shelves faced a sharp reduction in their living space. But that wasn't all. Falling sea levels disrupted the global system of ocean currents. The warm currents that had previously carried heat from the equator to the poles stopped. The oceans began to stratify. Warm water remained on the surface while the depths filled with icy water. This led to the disappearance of oxygen from the deep layers, and vast tracts of the ocean turned into dead zones. The planet was rapidly cooling. The ice caps on Gondwana, like a giant mirror, reflected sunlight back into space, only intensifying the cold. Tropical species accustomed to warmer climates were unable to survive this new, icy world. Ecosystems collapsed one after another, triggering a chain reaction of extinctions across the planet. This event, known as the Ordovician Silurian mass extinction, was one of the 5 worst in Earth's history. An estimated 85% of all marine animal species disappeared from the face of the planet. Entire groups of organisms were wiped out forever. Many families of trilobites became extinct. The vast majority of brachiopod species perished. Coral reefs were almost completely destroyed. Giant cephalopod predators like Anomalocaris disappeared forever. Underwater forests of sea lilies were devastated. The extinction occurred in 2 deadly blows. The first was dealt by the onset of glaciation and falling sea levels. The second blow came when the glaciers began to melt. It would seem that the return of water should have brought relief, but it didn't. Sea levels rose too quickly. The oceans began to mix, and anoxic toxic waters from the deep gushed into the shallows, poisoning everything in their path. The climate became wildly unstable, swinging from hot to cold. But life, as we know, is incredibly stubborn. Even after such a catastrophe, many managed to survive. The trilobites, though they suffered horrific losses, survived. Brachiopods, mollusks, and echinoderms. The survivors began the slow and arduous journey to recovery, and our humble heroes, the vertebrates, survived this apocalypse almost unscathed. They were ready to seize the opportunity the desolate world offered them. The Ordovician period was a time of great biological explosion and great tragedy. It demonstrated that even the most thriving ecosystems can be destroyed by abrupt climate change. It demonstrated the fragility of life in the face of global planetary forces. But it also demonstrated its incredible resilience. It was a demonstration of life's incredible resilience, its ability to recover, adapt, and continue its great evolutionary journey even after the most devastating blows of fate. Let's travel to the oceans of the Ordovician period. The scene that unfolds before us is full of true wonders. Imagine giant cephalopods, those ancient ancestors of squid, silently cutting through the dark waters. Around them stretch endless coral reefs, teeming with millions of living organisms. Here below, entire underwater meadows of crinoids and sea lilies stretched out, gracefully swaying with the currents. And along the very bottom, the first fish, clad in bony armor, slowly moved. This was a world where invertebrate giants reigned, a world in which vertebrates were only just beginning their long and arduous journey to dominance. But all this splendor was destined to vanish. The icy breath of the southern supercontinent Gondwana was already bringing destruction, cooling the oceans and preparing to forever rewrite the history of life on Earth. Approximately 444 million years ago, our planet began to slowly heal from a monstrous catastrophe. The ice sheets encasing the giant continent of Gondwana reluctantly retreated. As the ice melted, sea levels began to rise and water rushed onto the land, inundating coastal plains and creating new, vast, shallow seas. The climate gradually warmed, returning to more comfortable and stable levels. Life that had survived the great extinction at the end of the Ordovician period received a second chance. A new era began, the Silurian period, a time of great rebirth when surviving species began to reclaim the desolate expanses, launching new, astonishing evolutionary experiments. But the defining event of this era was something completely unprecedented: the conquest of land, a process that irreversibly changed the face of our planet. During the Silurian era, the continents remained clustered primarily in the southern hemisphere, although some had already begun their slow drift toward the equator. Gondwana remained a colossal supercontinent, encompassing most of the planet's southern landmass. To its north lay the smaller continents of Laurentia, Baltica, and Siberia, as well as several smaller landmasses destined to merge into a single entity. The ancient Iapetus Ocean, which separated Laurentia and Baltica, began to shrink. The two continents were inexorably drawing closer, preparing for a monumental collision that would result in the rise of the majestic Appalachian Mountains. The climate of the Silurian period can generally be characterized as warm and humid, although it was not as equable as in the preceding era. At the very beginning of the period, the planet was still feeling the cold legacy of the Ice Age. Temperatures were quite moderate, and climate zones were clearly defined. But as the ice melted and carbon dioxide accumulated in the atmosphere due to volcanic activity, the greenhouse effect began to gain momentum. By the mid-Silurian, the planet's climate had become practically tropical. Even at high latitudes, there was no hint of polar caps, and ocean temperatures in the tropics could reach an incredible 35 or even 40 degrees Celsius. Sea levels during this era fluctuated constantly, but were generally very high. Vast epicontinental seas, essentially shallow inland oceans, covered vast swathes of land, creating a veritable paradise for marine life. These warm, sun-drenched bodies of water were rich in nutrients, carried by full, flowing rivers from the continents. It was here, in these vast shallows, that ecosystems devastated by the mass extinction began to recover with astonishing speed. Coral reefs returned to the seas of the Silurian period. Tabulate and rugosa corals, the few species that survived the catastrophe, began building new reef systems. These new reefs were not as large or diverse as their Ordovician predecessors, but they grew very quickly, forming complex three-dimensional labyrinths that became home to countless creatures. Fish found refuge in the crevices and caves of these reefs. All manner of arthropods crawled across their surfaces, and sea lilies swayed on their peaks. The reefs became veritable oases of life in the open ocean. Brachiopods, bivalves that suffered greatly at the end of the Ordovician, began to rapidly restore their former diversity. New species continually emerged, occupying the ecological niches left vacant by the extinction of their competitors. Soon, The shallow sea floors were dotted with dense colonies of brachiopods, which, like living filters, purified the water and created entire underwater fields from their shells. Bryozoans, builders of elegant lacy colonies, also recovered from the blow and covered any hard surface with their patterns. Trilobites, whose diversity had significantly declined, still persisted in the Silurian seas. They were no longer the dominant force they had been in the Ordovician period, but they still played an important role in marine ecosystems. Silurian trilobites became more specialized. Some species adapted to life at great depths. Others learned to swim quickly, and still others became masters of camouflage, burrowing into the bottom mud. Their shells became more complex, acquiring new defense mechanisms and more sophisticated sensory organs. But the true kings of the Silurian seas were the nightmarish creatures known as eurypterids. These predatory arthropods, which emerged as early as the Ordovician, reached their peak in the Silurian period, giving rise to forms of unprecedented size and diversity. Just imagine, some of them grew up to 2 meters in length, making them the largest arthropods in the history of the Earth. A striking representative of this group, the giant eurypterid of the late Silurian, was a true monster of the ancient waters. Its long, streamlined body was encased in a tough chitinous shell. The enormous pincers on its forelimbs were studded with sharp spines, deadly weapons capable of seizing and tearing apart even the largest prey. These creatures were at the top of the food chain in the Silurian seas. They mercilessly hunted fish, smaller arthropods, and mollusks. Some eurypterid species were excellent swimmers, propelling themselves swiftly through the water using their broad paddle-like hind limbs. Others preferred the tactics of ambush predators, burying themselves in the sand at the bottom and patiently awaiting their prey. And some were so resilient that they could enter the fresh water of rivers and lakes, and perhaps even made short forays onto land, pursuing prey in the intertidal zone. Cephalopods also regained their diversity after the extinction. Nautiloids continued to roam the oceans, although giant, straight-shelled forms like Anomalocaris disappeared forever. Silurian nautiloids were more compact, their shells taking on a curved or spiral shape. They remained active predators, patrolling the waters in search of small invertebrates and unwary fish. Meanwhile, vertebrates made several major evolutionary breakthroughs during the Silurian period. Jawless fishes, or agnathans, continued to dominate the vertebrate lineage. Their armored representatives, the ostracoderms, became even more diverse. Some developed more streamlined bodies and efficient fins, allowing them to swim significantly faster. Others retained their heavy, bony armor and led a slow, bottom-dwelling lifestyle. But the most monumental, most revolutionary event in the history of vertebrates was yet to come. It was an invention that would forever change the balance of power in the oceans: the emergence of jaws. At the end of the Silurian period, the first jawed fishes, creatures with mobile jaws armed with teeth, emerged on the scene. This innovation was a game changer. Now vertebrates could do more than simply filter water or scrape food from the bottom. They could actively bite, grab, and tear their prey apart. Jawed fishes gained access to larger and more varied prey, opening up entirely new horizons. The first jawed fishes belonged to the group of acanthodians, acanthoda, often called spiny sharks. These small fishes, typically 10 to 30 centimeters long, had streamlined bodies covered in small scales. A sharp, bony spine protruded in front of each fin, which gave the entire group its name. Acanthodians were fast and active swimmers, hunting small invertebrates and likely not averse to the eggs of other fishes. They had large eyes, and their jaws were studded with small but sharp teeth. The Silurian period also saw the appearance of the first representatives of the placoderms, placodermi, or armored fishes. These creatures possessed massive bony armor that, like a shield, protected their head and front part of the body, while their tail remained flexible and mobile.